That was a stunning performance. The next inline classical dance is by Haripriya from CME.
मनोरथ पूर्ण चतुर निजगण शोभित मणिमय हार अजभव
That was really an outstanding performance. Now we have a folk dance by Priya Madhuri and Nandini.
కింద కూస్తున్నా మనసైనా ఓ ముద్దుకుమ్మ లొంగబోని వేసుకొని దొంగ చూపు చూసుకుంటా నా మనసు దోసినావే బొమ్మ That was an amazing performance, showcasing the spirit and energy of the community. Now we have a semi-classical dance by Himaja from CMA.
మట్టి మాయలలో నన్ను తగిలించితే ఎటులనే బోధు గోపాల ఎటులనే బోధు శరణు శరణు భూరమణ దయాకర కరుణ చూడరాగా కృష్ణ శరణు శరణు భూరమణ దయాకర కరుణ చూడరారా కృష్ణ ధరణిలోన జనమురమున వెలసిన నరహరిదయ రాజా గోపాల నరహరిదయ రాజా గోపాల నరహరిదయ రాజా.
That was really a wonderful performance. Your movements were so fluid and graceful, Himaja. Thank you. Now we have a folk dance on Bonalu theme by Vaishnavi, Yashaswini, Yojana and Dhruti.
ముట్టు హైదరాబాదు
DJ
నట నడుమ చార్మినారు
Raju
చార్మినారు కొమ్ము కింద
MKR
నువ్వు కొలువు తీరినావే బంగారు మైసమ్మ నువ్వు కొలువు తీరినావే బంగారు మైసమ్మ
కత్తులు బల్లెము చేతబట్టి దుష్టుల తలలు మాలగట్టి కత్తులు బల్లెము చేతబట్టి దుష్టుల తలలు మాలగట్టి పెద్ద పులి నువ్వు పెద్ద పులి నువ్వు పెద్ద పులి నువ్వు పెద్ద పులి నెక్కినావమ్మో గడ్డిపేట గడ్డి మైసమ్మ పెద్ద పులి నెక్కినావమ్మో గడ్డిపేట గడ్డి మైసమ్మ కత్తులు బల్లెము చేతబట్టి దుష్టుల తలలు మాలగట్టి కత్తులు బల్లెము చేతబట్టి దుష్టుల తలలు మాలగట్టి పెద్ద పులి నువ్వు పెద్ద పులి నువ్వు పెద్ద పులి నువ్వు పెద్ద పులి నువ్వు పెద్ద పులి నెక్కినావమ్మో గడ్డిపేట గడ్డి మైసమ్మ పెద్ద పులి నెక్కినావమ్మో గడ్డిపేట గడ్డి మైసమ్మ.
రావు తల్లి రేణుకెళ్ళమ్మ మేము రాజుగారి పిలవనంటే రేణుకెళ్ళమ్మ తూర్పు రాజులో రేణుకెళ్ళమ్మ దొంగుటి యాల రెచ్చినారు రేణుకెళ్ళమ్మ
The performance was really appreciable. We thank the cultural coordinators, Dr. Rupashri and Ms. Srilata, for their stupendous job. Thank you.
Moving swiftly from cultural rhythm to technological innovation, it's time to kickstart our technical feast. We begin with our first distinguished lecture, broadcasting to us online. We now take the honor of welcoming our eminent speaker to this august gathering, and let me take the privilege to introduce Dr. Arpan Pal, distinguished Chief Scientist and Research Area Head, Embedded Devices and Intelligent Systems at TCS. Sir has 28 years of experience in embedded systems, IoT, and signal processing. Sir received his PhD from Aalborg University, Denmark, and BTech and MTech in Electronics and Telecommunications from IIT Kharagpur, India. The topic for this session is Emerging Technology Needs. And to deliver this address, we are deeply honored to have Sir with us. May we connect with Sir? Over to you, Sir. We are connecting to Sir, and Sir will join in sometime over online mode. Kindly be with us. Sir, am I audible to you? Sir, we are audible to you? Sir, welcome to ICESAIS. Thank you so much for joining us online, and we are glad to have you here today. Thank you so much.
Is it visible?
Sir, are we audible from the other end to you? Hello, sir. Is my voice audible?
Yeah, I am getting some echo. I am getting some echo actually.
All right. Thank you so much for joining us, sir. Thanks for bearing with us. And heartiest welcome to ICSAIA. We will be starting your talk in some time now. Thank you so much for joining us online.
Hello? Okay. So is it audible? No? Is it audible? Am I audible? Thank you. So, good evening, everybody. So today, what I am going to do is, and I'm extremely sorry that I could not be there physically because of some unforeseen other meetings that I had, and so that's why I have to be online here. So, and thanks for inviting me. So what I'm going to do today is actually, I'm going to talk about sensing, but the sensing that I'm going to talk about is beyond what we know as sensors today, but more as what we call as intelligent sensing, or sometimes we call AI for sensing, which is basically at the intersection of sensing, computing, and AI. Okay. So with that as a background, so effectively, just let me define the sensing as a concept and why it is becoming important in this today's what we call as a cyber physical world. And I think in this conference, many of the things that we are going to look at is actually a cyber physical system. What we mean by that is actually there is a physical object and in the physical world, and usually we put sensors on that object to understand certain feature of interest of that object, and we observe that through signals. But the job is effectively is not understanding that sensor signal that is coming out. The value of today's world, where we call as intelligent sensing, comes when there's an external event that happens in that physical object, and through the from the observed signal, can I actually do the inverse and actually find out what event has occurred. So just to give a simple example, you are maybe in a room which is a physical object. I have put a temperature sensor there, which is, I would say, my sensors, and my feature of interest is the temperature. Sensor may be a thermocouple, and I'm getting a continuous signal on it. Analysis of signal doesn't mean anything, but suppose there's an external event of interest. Suppose things have something going wrong and something is getting hotter, and it may result into a fire. So my job in an intelligent sensing system will be to, from this signal, I actually invert and figure out what is the external event that is happening, or is going to happen. And if I could predict it, I could maybe prevent it. So effectively, intelligent sensing is to find the event from the sense data. It is basically the inverse. So effectively, if you see perception and signal, so signal is a function of the event, and this function may be the transfer function of the whole cyber physical system. But perception is basically nothing but getting the inverse. From signal, can I get back the event? In temperature example I gave, maybe it is very, very trivial, but in most of the, I would say, real systems, this can be a big, big issue. Okay. And because we don't even know the forward function. The F is not known, forget about X inverse. The value that AI is bringing now is, even if we don't know the F, which is a transfer function that hard signal a particular event will generate in a particular physical thing. Think of a human body, my physical object may be my heart, and my feature of interest may be heartbeat, and I put a ECG sensor. Think of, from there I want to find out whether I have some cardiac disease, which doctors do. So you can then will start understanding how complex is this part of it, that forward function is not even known, and the inverse is much more difficult. But given we can actually have trained AI models now, we can actually train function models that can directly learn that F inverse. And I can actually give enough examples of P and S, we should be able to do that. So that's the idea of any intelligent sensing system. And it has, you can see that devices has moved from basic internet consuming devices to IoT devices. Now we call it AIoT, AI and IoT coming together. And we see them very much prevalent in IoT, robotics, and AR/VR kind of spaces. And this is a very generic term, so it will cover a whole span of applications that we are going to look at. So now, why this sensing is important? So we look at sensing from a completely different thing, that over the past 2-3 years, we have this so much noise and hype about AI. But we think of sensing as a data generation infrastructure for AI. The core infrastructure for AI is their compute. We always talk about GPUs and other things. It is needed. But we are not realizing that if we don't generate the data, so data is the new oil. Everybody talks about it. That I would say sensing is the drilling technology for that oil. So if you don't have the drilling technology, you don't get the oil, isn't it? So the sensing becomes a very, very important pillar for AI. And why it is there? Because today, the majority of the AI we talk today as generic, that we talk about ChatGPT, large language model, Gen AI, they're all trained on mostly camera, audio, text data, mostly. And the reason for that is the data which already uploaded in the internet for last, say, 20, 30 years. We have uploaded 20 years at least. We uploaded that data. So most of the the so-called AI models are trained on only that data. And that is a kind of very consumer-facing application. If you really want to look at the cyber physical system and real enterprise level applications, we have to generate data which understand the physical world. And I think only camera and text will not do that. So we have to have more sensors. So we call it as a sensing across the spectrum. And there are different new sensing modalities we have to talk. And these are all examples I will give you to tell that why we have to go beyond standard sensors and build some new sensors which will have a better markers of those events that I was talking about. And in general, they talk about biological kind of a scenarios. You have to sense tissues, biofluids, gas, human body, and some non-biological things like vacant space, solid, semi-solid, liquid. So in general, we'll be talking about this. The challenge that we face here is actually when you create new sensors here, and where we are kind of looking at a downstream AI to make meaning out of those sensing data. One side, we have to kind of create a super sensitivity. So you have to make the sensors very, very sensitive, very, very high resolution, and very, very high dynamic range. Everybody knows it. So sensitivity should be high, resolution should be high, dynamic range to be high. But a challenge that comes in moment I make it sensitivity high, resolution high, and dynamic range high, we also allow a lot of noise to creep into the system, and which actually can be very, very bad for any AI to learn. AI is a dumb program which learns from the data. So if the data is not, if I'm allowing too much noise to creep in, the sensor, it may overfit into that and it creates problems. So while I make it sensitive, I have to also make the accuracy specificity better, and I have to make it robust. So this is one kind of scientific challenges you will face in any of the sensor design. The engineering challenges will be because you have to deploy in the field, you have to have unobtrusive or non-invasive way to sense. It may need to penetrate certain barriers, like it has to see through a wall, see through a box, see through the human body. It has to be in situ, it can be portable, it has to be real time, it still has to be smaller size and low power, and above all that, it should be affordable and scalable. Because now we are not talking about a very hi-fi sensing system, which is kind of sitting on $1 million system. It will be something that is, it has to observe the thing and it has to scale. So otherwise, the return of investment of this hardware will never come in the business. So keeping that in mind, so effectively, these are some examples I will give you where we have to create new sensing modalities. I'll talk about it, which can actually, these are, I would call the cyber physical system mapping. So whether it is so I think I'll give the examples, but effectively, they're actually kind of catching different properties of the cyber physical world, and each of them can give very, very rich information, which can lead to very value-adding application, and that is annual cover. Okay. So let me start with one, because I think the moment we talk about radar, we think of that as a more of a defense-centric application and maybe applied in many kind of large systems. But what we are seeing now is I use a very practical problem today, what we are facing. I'll just mostly talk about the application here. I will not go to the details of that, actually how we're doing it, but just to give a glimpse of the application. So the radar is basically needed to image inside a box. Why we need it? We need it for any security surveillance problem, maybe logistics. That suppose we are kind of shipping these cardboard boxes with, say, we have a problem one customer gave us is that there's a lithium-ion battery is not allowed to be shipped within the cargo. But without an X-ray machine, how do we detect that there's a lithium-ion battery inside the box without opening the box? It's a real problem actually there. So we thought that we'll actually use radar, microwave radar, but use a very scanning, raster scanning system and create an image out of it, which can be actually be used to understand what is inside the box. Okay. And even other problem that we are looking at is the robots in the warehouse today. Robots actually go and pick up these boxes. Very rarely you will see a human body people picking up boxes in an advanced factory warehouse. So now robots doesn't know what is inside the box. They don't know what is the center of gravity of that weight of the box. So they don't know what to hold in the box. And if they don't do it right, the box may fail, the robot may topple. And obviously, there will be a lot of time wastage at all. So effectively, in seeing inside a box is a very, I would say, enterprise-grade problem across industries. So what we are doing is we are taking a very standard radar model. We have both pulse mount radar and FMCW radar kind of a thing, very small, miniaturized. But what we do is actually we create the image, and you can start seeing that kind of image that you can see the top. If the image, actually the left side you have the camera image, and this is what actually we start seeing from the radar. If we actually image it properly with all processing and some kind of machine learning applied to it, you start getting a image and can start understanding what. Obviously, the quality is not that great, but it will be good enough to understand whether you are carrying a forbidding object in the or a robot to understand where it should hold as a center of gravity. So this is one kind of application that are coming, and we are seeing a lot of traction. We have a lot of applications coming in top IEEE sensors and other conferences where we see this thing begin seeing the new kind of applications that will come in. I'm not going to the detail of how we're doing it. It is a traditional radar signal processing followed by some AI ML that has to be applied to bring that specificity, sensitivity, resolution kind of a thing. And tomorrow, maybe we are also using generative AI. If we are doing it right from this right side image of the radar, we should be able to regenerate the optical image also. If we have enough example to train, that can be the next way to go. Same problem applied in a different domain of, I would say, biotissues. One possibility is that is a very big problem of all logistic, food security, all food logistic chain, how a food is going bad. And you can see this banana, you can start showing it is going bad if you see this right side 5, I would say, images, the blackness has started coming in the outside. So you can use a camera to detect. But I think it has not started much earlier. In the other images, if you see, it won't be caught in the camera. But what we do is we actually image it inside using the radar. Again, it's a conveyor belt, and it can be done single or it can be done in a crate. And when it got done in a crate, maybe there's one rotten fruit which actually can completely spoil the whole crate. And it usually happens that way. So can we catch it early? So effectively, that's what we are trying to do here. And in future, the same technology can be also used to image inside a body. And we are kind of looking at applications where, in usually imaging inside the body, X-ray is the way to go, but X-ray is hurtful and it cannot be portable kind of it's not really a portable device that way. Ultrasound you can do, but ultrasound you can do only in certain use cases. But think of that, can I do a brain imaging inside the skull? Because this microbe will penetrate. So can I do a very thing without, before you go for MRI or CT scan, can we do that? So this is the second kind of scenario that is there. Third use case we are working is, again, another sensing modality where, you have to understand the property of a liquid or a semi-solid. And what it means by that, 2 examples I'll give. One is the pen quality. We are working with some pen companies. When a pen gets produced in a factory, the biggest problem that they face is that they have to make a very, they have to have a very specific viscosity of that pen that defines the quality of the pen. And it has to be homogeneous. The viscosity has to be homogeneous across, and the color also has to be homogeneous. So these 3 properties they have to do. If this is not there, the pen quality is bad. Today, it can be done by, they take a sample, as they produce, they can take a sample of that paint in a container, take it back to a lab, do a test and come back. Usually it takes 2-3 hours to do that actually. So for those 2-3 hours, if there's some problem in the process, bad quality pen gets produced. So you have to either throw it away or it goes to the end user as a poor quality. So our customers wanted that, can we do it in situ as the pen gets produced? So this acoustic or photoacoustic sensing is a very interesting thing. You actually shine a laser pulse into that, I would say, the paint. The paint, it will, because the laser pulse is high power, it will actually kind of heat up the molecule of the paint around this. And because it's a pulse, it immediately cools. And when it cools, it actually emits energy, which incidentally comes in an ultrasound frequency. So by looking at an ultrasound receiver, so it's a pulse transmitter and ultrasound receiver, we can actually, it contains a marker of the property of that. So now that is what, so now this forward model or this inverse model is not very clear, how viscosity is linked to this. But if we can train this system with enough control experiment, that's what we are doing, we are able to build I would call a model, AI model, which from this photoacoustic ultrasound received data, which we can actually, what should I call? We can compute estimate of the viscosity. And obviously that will be very useful. A similar technology now we are working with companies like Coal India kind of a company, where it can be actually used to detect a very important problem, which is called spontaneous heating of coal. Coal, when it's stored together in a bunch, they burn on their own. And when it burns, it's a sustainability hazard. It actually creates a lot of issues. So can we actually predict it? So this is still not solved. We are working with IIT Dhanbad in that kind of problems. Another problem, because these are all examples of, I will tell, this intelligence sensing problems and how we actually need a small downstream AI to really understand. So this is a problem of, diabetes. It is basically pre-diabetes detection from human breath. Because when you are talking to the doctors, we realized many work happens where people want to detect diabetes in a non-invasive way, without you don't need to prick to get a blood. But when we talk to the doctors told maybe that is not a very large problem to do. People having diabetes, maybe still they're okay to have a finger prick to measure their blood sugar. It is okay for them. It is not a very path-breaking change. The impact that will come is when you can detect this, to detect pre-diabetic people in a non-invasive way. Because that is the part when you catch people, because those people will not go for blood test. The prebiotic level you can catch, a lifestyle change can actually make them not move into diabetes. And that is itself is epidemic scale. It is happening globally. More important, it is happening in India. So we thought that can we do it from human breath? Why new modality now comes? Because in human breath, these 4 gas markers, acetone, isoprene, isopropyl, and ethanol are the markers of diabetes, which is actually present in a sufficient way to detect by any sensor. Challenge is when pre-diabetic, they are present in an extremely low quantity. This part per billion they present. So we thought we'll use nanosensing, extremely high sensitivity. We're working with IIT Kharagpur, we built that nanosensor. Now the other problem came is moment you build a highly sensitive sensor, the other gases in your breath, because our breath will also have CO2 and O2 and nitrogen and everything. Those gases actually started to create noise in this. So effectively it is a high sensitivity, specificity, how do you balance? And we figured out that this can be only done if you actually train an AI model around that detection. And that's what we are doing. So that is the way we are trying to. So we have got some very interesting results in the beginning, and we have a device now, which are actually now doing it. We very soon will plan to go into a trial for this. Now coming to another very, very interesting sensing phenomena called quantum sensing. Because I'm telling the modality, I'm giving you pointers where data to them doesn't exist. So there's no point or there's no way there's a downstream AI which can make meaning out of it. This is an example where you can quantum sensors can they call it diamond defect sensors, that is their nitrogen defects. And these quantum sensors, basically, I will tell you in principle what did they do. They actually detect change in quantum state. And it is basically but the point is the quantum state is used also for quantum computing, but there this quantum state getting destroyed by, say, external magnetic field or gravity or movement, it is actually a problem in the quantum computing because this destroys the quantum states. That's why quantum computing is still not that mature today. But the very fact that this external change in gravitation field or electromagnetic field or movement can actually change the quantum state, can make them an extremely good sensor. At a femtotesla level, you can detect a change in magnetic field. So how are we using it? We are using it to detect. We can map the current inside a chip without really opening it. Okay, so we can map the current at different layers, and because this current mapping can happen at almost at a transistor gate level. That is the spatial resolution is at gate level, micron scale. The sensitivity is at nanotesla to picotesla level. And using this, then there's a lot of possibilities of detecting chip defects. In some cases, you may actually be able to detect trojans within a chip, hardware trojans within this. We're working with IIT Bombay and ICESAIS Bhopal on this kind of a thing in the National Quantum Mission. But this is a sensor, I think I'm not talking about detail, that has enormous opportunity. And many other things can be done. Mineral exploration, metal defect detection, pipeline corrosion detection. At an unprecedented sensitivity and resolution, it can be done if you can do this. But the signal that comes out of this is extremely noisy, and we need a completely AI signal processing pipeline to make any meaning out of it. Okay, that's what we do with IIT Bombay. Another example of this is a plasmonic sensing. I'll skip this at this point. I'll talk about it later. Another, I think, important sensor we feel it needs to be built is in the space remote sensing area is something called long wave infrared, or I would call it is a thermal hyperspectral sensor, which can actually understand, and it can basically what we are saying, it given a a good AI model to catch, we should be able to detect materials. And that material, two major applications. One is, can I detect pollution and pollutants from the space, from a satellite, just using no other sensor? We think it is possible. Another is mineral detection, rare mineral and other things. So those are two cases what is possible. The challenge here is usually the mirror that is required is very large in this kind of a wavelength, and that creates a lot of weight which cannot put on a drone or a satellite. But we are trying to see how the mirror size can be brought down, and that's what we are trying to look at and then create this kind of application. Finally, another application, this is my examples of new sensing. We are using a ear wearable which can do EEG. And why we think it is important is basically we can get brain signals when you are wearing a headphone. So on day-to-day, as you move around doing your day-to-day work, we are able to get the brain signal, and from that we can actually get different models you can create to detect, say, your cognitive load, stress, and that in turn can convert into a natural setting detection of, say, stress and anxiety and mental health problem for people. One direction. Other direction, this can be this is something we still don't know. We are working with Niman's is, can we actually detect dementia or Alzheimer early onset in a natural? Because today, if you do a MRI CT scan, it is done, but nobody is going to do MRI CT scan every day, or they will do it once a year. So it is not a very longitudinal way to look at it, but making it a ear wearable like a headphone, people can just wear it and we can actually see a trend in their cognitive decline and other things, which we think can be a very strong marker. And we are working with this also, the device, what you see as a picture is ready, and we will very soon go with a trial with neighbors to actually prove the first level efficacy, that is there really a marker of cognitive load in the ear signals. Okay. So given this landscape of, I would say, applications I talked about, which are all new sensing, but this is a representative set, that way all many new sensors needs to be developed. The other part we are trying to see, again, let's go back to the first diagram that I talked about. Again, I'm repeating it. But let's look at this perception and cognition. Why it is important is this is how our brain works. Perception is the immediate sensory process, where we don't really try to understand what it is, but we try to understand that physical world in some representation layer. Our brain, it can think of these are pre-trained models in our brain, which creates a representation. A simple representation can be, example of representation is, I see it and I put a camera and I get a picture. Understanding the picture is the cognition. So I'm giving an analogy. So now each of the application I talked about, I can actually now, first layer, I can just create a representation, which is the perception, and then I can do the cognition. Why it is important is, we are segregating the task from the actual sensing. Today, most of the AI system, they put those together and train one single model around it. So every time something changes, you have to create a new model. So these things are not foundational. So what we are claiming is that, can I now segregate perception and cognition, have one AI model for perception, and which is task agnostic, and have another AI model for cognition, which is task specific. And to signal processing people will relate to this very well. The more yellow I am more sensor specific and application agnostic. Data synchronization, calibration, signal conditioning, representation, fusion, basic classic signal processing things are more application agnostic. The pink ones are more application specific. We are actually drawing a line there. And we are telling for top one, we should actually, that is our perception model. The bottom one is the cognition model. We should have two AI models for this. And why it is needed, this model, so the top one, because it's task agnostic, they can be made low memory, they can be made extremely low latency, they can actually run on device. That's what and it can also go to the hardware. Whereas the later part is task specific and can go offline into the cloud and all other kind of scenarios. Okay. And that's what we call as a sensor specific foundation model. And anybody who is now, I don't know how many people they here actually are familiar with the large language model, the OpenAI, the ChatGPT, and other things. Today, what you see as a proliferation of that, around 22, 23, they came out. All of them came out because in 2018 there was a very fundamental work that happened, what they call as text representation model or text foundation models. There's something called BART. You can Google it, BERT. BART was a transformer model which was designed to represent text. And it was a universal pre-trained model. The ChatGPT, the P is for pre-trained, okay? The pre-trained means I don't need to retrain again. It is foundation. It's trained once on a lot of data, it just works. So it creates a representation, and from that representation, you get all kinds of applications today, which is today's world of, you can talk to, there's a chatbots, you can generate code, all those applications are coming out. So it took 5 years for create those applications. What we are telling is you have to build BART equivalent of every sensor, okay? That's what it is actually, that every sensor there will be a BART equivalent representation, followed by specific task of what applications are going to be. So, and this actually we presented in this year's ICESAIS, the Signal Processing Conference, very well received. So we're trying to see how we can take it to the next level. We are calling it the sensor-specific foundation models. Okay. The other part where AI is going to be used, and that is, I would say, is any design where the output of the design is a layout. So think of this as a, say, any antenna system or a plasmonic system. We design these layouts, and output of that layout is some kind of frequency response. Okay. In antenna, it may be your beam width or a beam thing is the output, but you have antenna design that is going to come in. Okay, the same thing. There's a beam and there's an antenna design. And so if we have enough such designs available, this is a forward. I think given a design or a layout, I know what is the output specification. We can actually create an inverse model, but given a specification, I should design, basically create the layout. And today the technology exists. Today, whenever you are drawing something in a generative AI with ChatGPT, this is the, instead of what you are drawing is a 2D diagram, which is very similar to a layout. What you are giving is the input instead of this kind of a frequency response, which is a byte array. I am giving a query, text query, which is also a byte array. So effectively, that technology today exists, but this can be actually used for scientific designs. And we are seeing many examples here, which should be possible here. Okay. So now, as we understand now, the part is that now we understand that we have to do a lot of sensing, will need a lot of onboard computing also, because we need to get this low latency, then kind of a thing, but we have to make it interpretable, all those things. So now the other part that is coming, that for the onboard computing, we have to now start thinking that can we run AI models on small hardware? And it is not something that is a generic thing. It is really becoming the problem that world is now facing. You have seen that OpenAI loses, today also there is a case, so they are losing money. And they don't know why they are losing money. They are not losing money because their GPUs are costly, they have to do anything. They are losing money because the heat generated in their air, the cooling cost and the air conditioning cost, those actually the cost is so enormous, and you can see the value, training energy cost that is going. GPT-4 itself is 50,000 megawatt hour. So any of this, you can start thinking there's so much energy that's needed. So we have to look for now resource. So AI is today using infinite resource and is not going to scale. So none of them are going to sell. All of them are making loss because it actually is a problem. So now the point is we have to look at AI, which is resource efficient. One way, in the cloud itself, they should consume less power. On the other hand, like the kind of intelligent device I'm talking about, you have to create very small, efficient models, like the examples I gave, but it has to run on, say, a microcontroller or a very small signal processor that I have on board on I would say, any kind of a robotic system or any kind of a moving system. Okay, so in all those kind of scenarios, I'll need a very, very small AI model. So this resource efficiency is a reality which will make or break tomorrow's AI to scale. Okay, there is a barrier that you have to look at. So one way to look at it, and something that you have solved, you can start seeing three examples here. In one case, it is the first one is a card assembly line where you have to find out the defect. Again, the defect has to be found in real time. So latency is the biggest problem there. Second use case is an extended version of that in a outdoor, which is you have a customer who is a pesticide company. They have a car which is now detecting automatically through camera there is there a weed or a crop in the field. And if it detects a weed, it has to spray the pesticide on the fly. The point is the car, that tractor is moving, so I have to detect within 50 milliseconds that yes, this is a weed, and then spray. If I delay more than that, I will spray on a good crop than rather because I moved on. The third use case is actually a wearable or a smartwatch based heart ECG detector, which can go as implantable or a wearable. So all these three cases, which need a very small thing. So all these three cases, they need very, very low and very low latency and low size AI models. But we'll need AI. Pure signal processing will not give you the kind of generalization we need. So we are kind of trying to work in that space to create that kind of thing and see the kind of model size reduction and latency reduction we are able to do in that. And we are able to now create, say, even language. We have got these large language models, but these things are there. They are trillion parameter models. So we have now worked with what we call a small language model, SLMs, which can run on your mobile phone. No internet connectivity required. And it can run on your mobile phone. So it is completely privacy preserving thing, which can now, we have trained it on cardiology specific data. So it can become a cardiologist's, I would say, helper without any data connectivity, without any data leaking out to the cloud. It can onboard, it can actually, it's almost like a chat GPT on your phone that only understands cardiology. Okay. And it's possible to do that. And we are trying to do that and again trying to deploy it. The other angle of this whole story of this, I told this is creating small model is not good enough because the energy is still may not be small enough. So if you want to look at the energy that is small, okay, look at our brain. Our brain in this card, if you see, our brain consumes around 20 watt of power, okay, to do whatever we do. A GPU and CPU, we are in the, I would say, megawatt and gigawatt of power to do the same thing. Why it is that? The reason of this is actually fundamentally the architecture of our current compute system, which is, I think, it is almost how much? 30 plus, almost 50 years old. Beyond that, 1970s, the architecture of microprocessor came out. We are still following it, which follows a concept called von Neumann architecture. And any other architecture is basically a derivative of that, where you CPU and the memory is actually separated in two buses. So you store the data in your memory, your CPU's compute is in one place. Every time you want something, you fetch the data from the memory, compute and give it back. That is very good when you used to do logic programming. Pre-AI era, logic programming, it is okay. You just see if A greater than B, do something. And the do something is a more bigger task. So fetching A and B is not a problem. In today's AI model, I am doing millions of, I would say, if I have a billion parameter model, I'll be doing billions of multiply and additions. That's all. So I do A into B plus C. So ABC are shown in memory. So this backend, so every multiply and add is I will compute. There are 9-10 cycles of back and forth of data that goes from the RAM to CPU. This movement of the data is what actually causing that gigawatt power. And this is what actually ultimately causing OpenAI to lose that money. Think about it. So effectively the heat is generated because of this movement. So neuromorphic computing is actually gets inspired by your brain, but you tell you don't allow the data to move, we'll collocate memory and compute together, just like one neuron in our brain. You have one small compute and one small memory together. It's called in-memory computing. And followed by, in sensing part, we actually work on spikes. We only work on change. Our brain only work on spikes. That if I am only there is a change, I get a set of spikes. And then you generate a neural, you actually use a neural network downstream, which actually understands those spikes instead of normal data. It's called spiking neural network. It's much more difficult to train and understand the spiking neural network, because the very fact that the whole, I would say, neural network principle, AI, the machine learning, deep learning models are based on a concept called backpropagation, which kind of differentiates the error to find out a gradient through which you optimize. If you work on spike domain, spike is non-differentiable. So the backpropagation current form doesn't go. So it's a whole new area of science. This is something we feel is become very future for extremely low power sensing, because power reduction is at 1000x. We have hardware in our lab which shows that. So this is something going to be the future. Okay. And one interesting thing is you actually participate in this CII Design Excellence Award, and we got the best Big Tech Award this time. And I think there's still somewhere to go. We are working with IIT Delhi, Kharagpur, and also IIT Bombay there. But I think this will be the future of the AI hardware coming. Now, quickly, I think I talked about the technology, so I'll quickly walk you through some of them, because I'm coming from the industry. So just give you a flavor of the applications that we are going to enable using that, because I talked about the sensing and the compute technology as underlying. And there will be three kinds of application. One part is that understanding machine material infrastructure, what I would call non-people world. One is understanding the people. Basically, it is both clinical and non-clinical applications for this. And understanding the earth. That can I look at the earth and sense it, basically remote sensing applications. So human, earth, and machine material, this is basically the objects you are observing. Okay. So one application we are doing is, we call it sensorium, but effectively think of this as an extremely multimodal sensing application, which can say, we can take a camera data, it can take your telecom data, it can take other kind of data. It can take all data together and fuse it together to actually start modeling the physical world. So one big application we are seeing in the law enforcement border. So that's where we are working with law enforcement and defense thing people there. But there are also other applications that are going to come, maybe in smart city, rail networks, and many other cases, which we are going to look at. So this is one kind of, I would say, broad scale. So having those sensors, that how you actually put it together to really create a end-to-end application is very complex at that level, and you have to handle that. The second application is actually think of that machine material kind of a sensing, where I'm giving two examples that we are working with some of the applications where these ball mills that are there in many of this, anywhere you need to crush iron ores, crush for cement. They crush it by having this large cylindrical rotating mills within which you have steel balls, and you have the ore given to be crushed, and they rotate and the balls hit that and do it. But as the ball hit the ore, it also, they themselves get eroded, and they also hit the, I would say, the wall of this mill, which is the liner, and they damage it. So the challenge is, these are multi-million, multi-crore rupees equipments. They run 24/7. You don't know when it is getting damaged. So it is a classic predictive maintenance. We are trying to see whether we are trying to, can I look it from outside? Just by hearing the sound, using a microphone array and looking at vibration using laser and radar, can I model what is going bad inside? So it is a very classic example of, can I look from outside and still do a predictive maintenance of what is going on inside? And this is an important problem for most of the factories. We are working on it. I already talked about the paint thing, but now we can see this is a real paint factory on which is going to deploy. These are the thing. Think of this cylinders in which the paint is getting produced. Okay, you can see the left bottom. Within this, we are going to create a small window, and in that window we'll deploy our photoacoustic sensor. It will look through it, and it will immediately in situ predict. This is the signal that you get for photoacoustic. From there, we are going to predict the viscosity. That is what we are working on. Okay. Health, I talked about ECG and all. Same thing, that can I now, using very simple modalities like your oximeter, ECG, and heart sound, can I actually model my heart blocks? Because heart block is the biggest challenge that we face. Before actually, because people will do an angio to get it, but how many people go for angio in the beginning? So can we actually do it? And we are working with Cardiological Society of India. We are on a 10,000 patient trial. We have already collected more than 5,000 patient data. So can we replace, I not call replace, can we create a screening for angio using this, which can be deployed with ASHA workers at, I would say, primary health clinics, which can actually tell people to when to go to a cardiologist specialist and do an angio, that kind of a problem. Okay. The last application I have is a very interesting application, non-clinical application of people sensing, where what you see is a advertisement. Today, and it is going to create the advertisement. They are evaluated using a concept called A/B testing. So people use questionnaires to do it, and the feedback from that they used to treat the good, bad, or bad ad. What you hear today, 2 Tanishq ads, they passed through the A/B testing, both very well. And one of them actually fared very well in the market, one it didn't. So what we thought is, can I now sensorize it? Basically what we have done, we have used eye, gaze, and we have used an AI-based model to look at the blink of the eyes and the blink rate variability as a measure of attention. And what you see is a plot of the attention and the hotspots of where I am looking at as the whole frame-by-frame view of the whole ad. What you start seeing now, effectively, the left side ad actually had a very good attention, homogeneous attention. And it was attention was getting in very, I would say, realistic places of where the ornament is and other thing. Where anyway, any ornament company will want you to look at as a good ad, as an ad. The right side ad was actually A/B testing told it is a very good ad, but we found a lot of variability in the attention. And it was attention was all coming in the wrong places. It was not in actually the play of the, you can see it here, the attention is not really coming in the where the jewelry is. It is actually a very good story. People are, attention is here, not in the jewelry. So effectively, if you see, this was one of the best ad that was produced by Tanishq. The right side is one of the worst ad that was produced by Tanishq. It didn't convert. So what I'm telling is now, can we now do it early? Before that is, go to the market, can we evaluate this way? And in future, with generative AI coming, can this feedback be fed into a generative AI to auto-generate the content of the ad? That's a much more futuristic, but maybe it is possible as we go forward. So this is a very interesting application of human sensing in a very non-clinical application, but huge commercial value. So I am kind of in the end of my talk now. So I talked about a lot of applications, but the reality is, think in this way. We are talking about AI to control machines, maybe driving autonomous ground vehicles, predicting people health, monitoring plant process, ... That's what I talked about as an application. But it is really different from asking ChatGPT a question or understanding a voice command by Alexa. ChatGPT hallucinates. If I ask it 10 questions, once it will give wrong answer. Same thing happens with Alexa. If it is a non-critical application, I don't bother actually, isn't it? I don't bother if ChatGPT gives a wrong answer. But think of it, because I am now creating mission-critical applications here on the left side. Error here is actually can cause harm and deaths. So that is one angle that you have to figure out. There is a cost to the error of the AI. Second part is, yes, we have to understand the AI will make mistakes. No AI is perfect today. Then who takes the liability of this error? So this error liability cannot be lying with machine. There has to be human in loop. So what I mean by that, if I give that example of using ECG and oximeter to predict if there's a heart block, that cannot be a thing that can be prescribed to a doctor. Yeah? This can be given as a suggestion to a doctor. Doctor may suggest, okay, this seems good, yeah, that I correlate with other things, and then tell, okay, I think there's some problem, go for angiography. But a doctor will never take a liability of a false classification by the AI unless the AI model is interpretable and explainable to the doctor or the subject, so-called subject matter expert who is the human in them. So now today's AIs are black box. They are not interpretable explainable. So effectively, I would say reducing the error, understanding the liability, and making it interpretable and explainable so that the human can actually take it is the future. And to do that, you have to generalize, become robust, and remove bias, which I talked about. Ultimately, it goes to the foundation models, which are explainable. Okay? This is the need. And I don't think in the cyber physical world, we are not even 1% in there, if we talk about all these requirements that are there. So this is the next landscape of.
Sorry, sir.
With that, I'll end. So some of the things I talked is very, I think, a couple of years back, the 2 interviews I did with, one is IEEE Computer Society, their magazine, and the other was the IEEE Signal Processing Newsletter interview. I talked about many of these things. It is more about why and where it is progressing. Today it is actually happening. And the books wise also same as the IoT book one is there, which is more horizontal, but how it is applied in healthcare and how it is applied in manufacturing. These are the 2 things that are there, which can actually give you a very view of the use cases that are actually driving this in this world. So with that, I'll end and maybe can take some questions. Thank you. Hello? Hello? I hope my talk was completely audible. Yeah. Okay.
Model, as I understand, that one is of non-stationary as well as stochastic nature. In addition, sometimes we may have to chi-square and all other kinds of failure detection and then find out where is the target. Your perception model, who will build?
So there are 2 parts to it. One part, the perception model is not going to actually find out the target. Perception model will never find out the target. It will create a representation or an image or a visualization of that sensor data. So suppose I am using a radar scan. Let me give you an example of that inbox imaging I was doing. So we are having a radar scan, but from there creating a image like I showed the radar is basically the perception part. But I don't really detect whether there is an object, whether it is a scissor or a knife or a battery, is the cognition. But today, the problem of today's AI is it tries to do both perception and cognition together. That's why you end up, and we all know that if we use AI model, if you have enough examples, it actually is a nonlinear system. It generalizes much better. Even without understanding the it will inherently adapt to the distributions of all those you are telling. If I have the examples, it will adapt to those distributions.
Should I interrupt you once?
Yeah.
There are one model which is FFT. Hold on. Just one.
Yeah.
One model, first of all, will be outliers.
Yeah.
You know outliers, which based on your experience, you'll reject it. Then you will have your frequency-based FFT. Okay? Then you have...
These are not, I would say, these are transformed.
I'm just asking.
Yeah.
AI may, all these things I want to do. Now, after that, you are taking stochastic and nonlinear, all the things. That also, nonlinearity, there are ways of techniques. Output equation can be made linear, space equation can be perturbation based.
Yeah.
There are ways of overcoming that. Then if you read through Singer, These are all discussed. So perception model should have all these. Your neural network should be developed based on one part this, one part the other one.
No. What I'm trying to tell, the perception model also will have a neural network.
Huh?
Perception model of future will not have this signal processing. FFT is a transform. Okay, and perception model itself will be a neural network which will learn the signal and the noise and its properties and represent that in some representations
No.
there.
We can discuss in detail. But what I'm trying to say,
AI neural network which will understand that. That is the cognition.
what I'm trying to say, one is model-based filter, another is your thing. What you are talking is a database filter. But
Yeah.
database filter, neural network should take the extrapolation and other algorithm. Which
No,
is
not necessarily. The physics of sensing will be
I've seen
neural network now, which can be trained on physics.
physics
So,
with a difference equation. I've seen that. I've
Yeah.
seen that. I've
Yeah.
seen that. I'm telling you, my experience. I'm telling you. So that one also can be built.
Yeah.
This thing is, please, TCS should teach all these things to all of you. You are quite young, so exchange of ideas are required. We should
Yeah.
not be rigid with our ideas. You have told a very good lecture. Okay, I wanted to debate more when you meet personally. Thank you for giving such a nice and educative lecture. My question is over. Now Dr. Saraswat has come. I receive him. You talk to him.
Okay. Thank you. Is there any other question?
So thank you so much for having such an enlightening lecture. You have really truly set a high benchmark for the technical discussions to follow. Thank you so much and thanks much for this lecture. Thank you.
Stopping off.
All right. Thank you.
Thank you.
Carrying this momentum forward, our next session dives straight into the frontier of intelligence, AI cutting-edge technology. To decode this for us, we have global tech leader joining us all the way from across the world. Let's welcome Dr. Masi, Principal Engineer, Cisco, San Francisco, USA. Dr. Masiddin Mohammed is the Director, Principal Solution Systems, San Jose. His core competence is reflected in AI networking and infrastructure, strategic leadership, and is a technical expertise in various fields. And is a winner of Pioneer Award, RAS Award, and is a recipient of 50 plus internal recognition awards for technical excellence. Over to you, Dr. Masi.
Hello everyone. I wanted to thank you for the opportunity provided to me to speak on this occasion. Hello, can you guys hear me? Okay. As part of the agenda today, there are 3 topics I wanted to discuss. I wanted to go over the AI infrastructure landscape. Then we will go a little bit into how the AI networking for both front end and the back end has evolved, and look into some of the challenges and some of the futuristic solutions that we have in place. Hello? Hello? So when you look at the slides, you would see that artificial intelligence have touched every part of the industry, whether it is a government, manufacturing, finance, healthcare, and retail. And pretty much, I'm sure every one of you know, there are different use cases for every of these verticals that companies can use AI for. For some of these use cases, you have to build the models. For you to build the models, you have to train the models. To train the models requires a lot of compute resources and network resources. Apart from doing the model training, there are other training that you do, what we call it as fine tuning. There are 2 to optimize these models. You can do either fine tuning or you do RAG. RAG is regenerative augmented generation. Basically, you are responding to the queries based on live data, whereas you're doing fine tuning based on the existing model data you have. And then finally, there is another training called inference, where you are using this trained model for inferencing. What are the trends that we see today in AI? What we see is agentic AI workflows. We have moved away from ChatGPT, where it is supposed to just give a response to a query, to agentic AI workflows that can do some actions, do complex tasks. We have seen the rise of small language modules. We have moved away, we have not moved away, but we have seen large language modules in the past year or so, but now we are seeing a rise of small language models that can be used in a lot of inference edge AI use cases. And you have heard it in the previous lecture as well. One of the other important trends that is going on is the AI-powered cybersecurity. This is one of the most critical trend that is happening recently with the, you might have heard about Mythos model that has come up, where it could run and find vulnerabilities in any of the systems that exist in this world, with even if it is like 20-year-old or so. So this side of cybersecurity models that exist, so this becomes more an attack surface as well as mitigation tool. This gives an opportunity for hackers to actually go ahead and hack your systems if you use these set of tools. So our systems needs to be built with cybersecurity in mind going forward, which is one of the other critical aspects. A lot of companies are today focusing on putting cybersecurity guardrails in their systems or in all the applications that they build. AI infrastructure evolution, that is I'm going to talk, that is going to be the crux of the discussion that we have. We will talk. Also, we are seeing a lot of growth of AI networking in AI ops. Right now, with the amount of data that exists, with the amount of telemetry you can actually get out of your system, you could create predictive analysis, you could do mitigation, you could do triage, you could do resolution of the problems that you see in real time. You can also build agents that could do all of these activities for you. So observability, automation for running your AI ops has become critical for many of the companies that are out there that are investing a lot of resources. And finally, the sovereign and private AI. A lot of companies have data that is their own IP. They have built their own models. They wanted to have those models in their own vicinity, that they wanted to maintain the sovereignty of their data. So these are the set of trends that we are essentially seeing in the past couple of years, say from 2024 up till now. What you see, these are from 2024 to 2026. If you see, you can consider this as more of an AI trends across all the layers. At the bottom, you have compute, where you have moved from general GPUs to specialized liquid-cooled accelerators. From a network aspects, we have grown from 400 InfiniBand to 800 gig or 1.60 using Ultra Ethernet capabilities. From a cooling point of view, because of the amount of heat, amount of power that is required to cool the systems, we are moving away from air cooling stuff to liquid cooling capabilities. The location point of view, we are moving away from cloud hybrid to edge inference. And finally, from a software point of view, we are moving away from single large language modules to essentially multi-agent autonomous workflows. So these are the trends we are seeing for the past couple of years, and this is probably going to be there for probably another year or so before something else comes up. How would you run all of those things that are there in that layers that you have? I think the network becomes the most important part. We know that AML, AI, and MLDL are actually very, very demanding. Why they are demanding? There are essentially 4 tenets you will see in the slides. One is massive parallelization. That means you have GPUs that are actually doing jobs in parallel. Thousands of instructions are getting executed in parallel. You need the desire for distributed computing, where a single GPU is not enough. You have to have a network of hosts. You are actually need to build a network to actually do distributed computing. And these networks have to be highly scalable, and that requires a lot of bandwidth when you build these data centers. And finally, these networks have to be highly efficient, and that provides low latency. These are essentially the 4 major tenets for running your AI, ML, and DL applications. It's actually more iteration of the same stuff. AI workloads do not tolerate latency. That means you need to have the network which provides the lowest latency to run your data center AI networks. One is low latency, second is high throughput, and it has to be lossless. The bandwidth has to be highest bandwidth, because we are growing, the amount of network capacity is increasing every year. So the bandwidth needs are actually growing exponentially year over year. And finally, congestion management. We cannot have drops in this network. A drop could have significant impact on the job completion time. So we need to have mechanism in place where you can manage congestion management of the network. I just wanted to differentiate between how does a front-end data center looks and how does a back-end data center looks. When you look at a data center front-end network, what is the purpose of a front-end network? Essentially, historically, it used to be connecting your servers, whether it is CPUs, x86, and obviously the front-end data center typically used to connect to the internet. What are the drivers for front-end networks? One of the major drivers was migrating to the cloud, as you have seen with AWS, Microsoft Azure, GCP, Salesforce, and all of those companies that were providing cloud computing services. And obviously, because of that services, the bandwidth requirements actually grow year over year, and the interconnect have stayed predominantly Ethernet. So at this particular stuff, at the bottom you have your rack, and the rack you would have your servers, and then top you have the top of the rack switch, and then there is a spine. This is how, and above all is like DCI, data center interconnect. You're trying to connect between two data center, it's like DCI. So that obviously connects to the WAN. This is typically how your front-end data center actually looks like. There could be other designs, but this is one of those designs widely consumed. Then, what is a backend network? The backend network purpose essentially is to connect to a specialized units like the GPUs, storage. They do not connect to the internet. That means they are in the vicinity of a data center for the most part. What are the drivers for AI, ML backend networks? HPC, high performance compute and storage, AML explosion, increased bandwidth. What are the bandwidth needs because of the explosion? Year-to-year network increase, massive new build-outs are happening. From an interconnect point of view, proprietary is InfiniBand that has been there for a long period of time. Now people are moving slowly and slowly. Majority of the deployments are beginning to happen in Ethernet, where there was a massive investment. So when you look at a front-end data center, how would the traffic flow happen? So at the bottom you have a servers that is essentially this is a kind of a class topology where you have two spine leaves and say 4 leaves, 2 spines and 4 leaves, where the servers are essentially connected to the leaf. The kind of traffic that you typically see on a front-end data center is you will see a lot of higher number of flows with variable packet sizes that normalizes to a network bandwidth that averages over time to a certain level of say 70% or 80% of link utilization. This works really, really well for front-end applications because the entropy is high, the amount of flows are actually larger. How does it differ on a back-end network? When you see a back-end network, I'm taking an example of one of the collectives, already used collective flow, where one GPU is essentially sending transactions to all of the GPUs. When you look at the network bandwidth over time, you will see spikes pretty much at the same time. You will see the network bandwidth is pretty much consumed, all being same at the same time. Now, if there is a small link failure in the GPU on the same flow, what would happen is there is something called staggler. That means one of the links has failed, one of the GPUs stopped responding. Because of this, the collective gets hung, so that if you look at the network bandwidth over time, it dropped considerably. So we have to make sure when you run a GPU kind of based network that you don't see any of these drops or failures. This is essentially a reiteration of the past 2 slides. So the way the GPU operation works, as an example here being an all-to-all collective, you execute instructions on the CPU that is like high bandwidth compute that can saturate your links. The instructions are essentially processed by the GPU. You notify all other GPUs the results of that your processing, of your computation, and all of the GPUs essentially do synchronization. Once the synchronization is come, if any single of them is actually late, it impacts your job completion time. So computation stall for the slowest part. So when you look at the traffic patterns, there are too many asynchronous small bandwidth flows, chaotic pattern, you come to a consistent load. Whereas when you look at the GPU traffic, you will have small number of flows, but they're efficient flows. Because of that, they have very small set of entropy. So the load balancing decisions has to be like really designed well, so that you can get the optimum capacity of your links. there is a fundamental difference between your front-end traffic, front-end network traffic, and the back-end network traffic. I'm pretty sure you have heard about Rocky, RDMA over control Ethernet. This is essentially a protocol that is used pretty much in all AI applications. This is different from your traditional packet processing that happens where you have to go through your TCP/IP stack when your application talks to another application. Whereas in a Rocky, you are essentially bypassing the CPU kernel altogether. It means an application is talking directly to an application. Because of that, you will have lowest latency. So this has been pretty much the protocol that is being used for all your RDMA or AI traffic. So the RDMA NIC essentially provides non-blocking lossless Ethernet. Also, there are certain congestion management techniques that you use called PFC and ECN to make sure your network is not congested. This is essentially the same from a networking layer point of view. You have three different set of networks, where on the cloud DC you could have something called a scale up and scale out domain. I'll come to about scale up and scale out in my future slides. And then there is edge DC use cases or IoT edge use cases. And then from the scale across point of view, that means you're connecting between a DC to another DC. And then from a connectivity and control point of view, you have agentic networks, gateways, MCP proxies, and AI security. And then at the top, you have all the models that you actually consume. This is a case, I want to give an example of this is a case where one size does not fit all, because the requirements of every customer is kind of different. A hyperscaler requirements are different from a new cloud versus an enterprise. What hyperscalers care about is east-west traffic explosion. They care about capacity planning and energy efficiency, because the cluster sizes, everything they do it at that scale. They care about the GPU performance, observability scale, and reliability at scale. Neo clouds are competing against hyperscalers. They want to create a differentiation. They are the one who provides GPU as a service. They essentially provide the space and the power and the GPUs. They want to create a unique value proposition where everything is automated as a standardized networks. They can actually build any customization they could do, and they provide lifecycle management for these networks. And for the enterprise, the thing they care more about is automation, security, performance, readiness, cost and sustainability, and so on and so forth. This is an example of what has happened in the past few years. The scale of the clusters that has grown from, say, 2019 to 2025. So say in 2019, we are only doing content evaluation, image recognition, where the size of the GPU cluster, say, was 128 or so. Then it came 2022, 2023, the size have grown from 2K to 16K GPU DC clusters, where we are doing a lot of recommendation and ranking with Gen AI. Things have just grown up, where the size of the clusters keeps on growing. In 2025 and beyond, it is going to be more than 1 million GPUs cluster that is going to be in operation. So the fabric that you essentially build for the network has evolved because of the evolution of the number of GPUs, the higher number of clusters you wanted to run. Initially, we started from the class topologies. We essentially moved from InfiniBand to Rocky clusters, essentially all class topologies we just discussed a few minutes ago. Then we moved to DSF. I'll come into more details about DSF. It's essentially called disaggregated schedule fabric. which we build using fixed switches. And there is also something called non-scheduled fabric, where we use shallow buffer switches to build these kind of networks. So this is an example of, this is an actually deployed example of a use case where we have built a 4K GPU cluster for some of our customers that have 2 hosts on a given rack. That means each host would have 8 GPUs for a total of 16 GPUs. And then you would have 252 rack switches connecting to 18 of the spine switches. The 18 spine switches are essentially modular devices which provides 288 ports per single line card for one of the spine chassis. 400 ports. Basically, this topology will create a 4K GPU cluster for you to run your training or inference clusters. The features that actually you enable over here are PFC features, priority flow control, ECN, and IBGP. These are essentially predominantly features that from a software point of view you would actually deploy. For these, from a subscription point of view, it is a 1:1 subscription from the leaf to the spine layers. When you go forward, if I want to build a 24K GPU cluster, what I would do is I would just create 6 of those 4K GPU cluster, and also have another layer on top, what we call a super spine, and I create a 24K GPU cluster. What are the problems of having a 24K GPU cluster? So essentially all of them relies on ECMP, and ECMP, because the number of flows are very, very less, that means the entropy is less. The entropy is less, you will have a lot of hotspots. Because of these hotspots, it could cause congestion on one link, whereas the other links are unused. There are also a case of a microburst where, because of the burst, a single flow would be probably multiple flows trying to use one single link as its destination. If you have shallow buffer switches, they essentially can drop packets during microbursts. And PFC can lead to head of line blocking if not configured correctly. So these are some of the class network limitations. Because of this nature, we thought of actually going to how do I solve the problem of ECMP where the load balancing is not accurate. We devised a lot of methods, but we have to think about building a new set of a network to solve these problems. That is where DSF comes in. I'm not sure whether folks have worked on a modular chassis. If you have not, I'll probably skip. So a modular chassis, if you just take a look at it, it's essentially a set of line cards which you can consider it as the leaf devices which I have shown in the previous slides. And you have route processor which essentially does all the control plane processing. You have your fabric cards, you can consider them as your spine switches that I have shown in the previous slides. And then you have your PSUs and the fan trays that are needed to power up and do the airflow stuff. So if you have a modular chassis, this is essentially a scheduled fabric. That means it's completely 100% load balanced. You will not see any issues when you're running these kind of networks because of the nature, the way the backplane is actually built on the fabric devices and the leaf devices. You will not see drops, or you will not see imbalance in load balancing point of view. How do I replicate the same methodology using fixed switches? And that is where a DSF has come into picture, where I am decoupling all the capabilities that are there in modular chassis and essentially now putting it on fixed. The reason why I am to go to fixed is because I want to scale out. Because the modular chassis can only do so much. If I want to scale out, increase the size of my network, I need to go scale out domain where I have to only go with the fixed switches. So this is how the packet processing happens, where you would have virtual output queues. Concept of virtual output queues where the buffering is essentially happening on the ingress line card, whereas from a VOQ point of view, there is a credit grant mechanism that goes through from ingress to egress. So an ingress basically sends a request to the egress device. Hey, I want to send packets to you. Can you act? Whether you have enough amount of buffer to accept that packet. And based on that, the egress side of the stuff essentially responds back with an ACK saying that, hey, you can send me this packet. That is how the packet essentially goes through. Packet processing can be done in like two ways. One, it could be packet based or it could be cell based. When I'm saying a packet based, that means the entire packet, in this case, a 4K bytes essentially going to the device. Whereas if I'm going a cell based stuff, what would happen is the packets are essentially broken down into cells in 256 bytes, where it is very, very uniform from a packet processing point of view. So this is how the DSF is essentially born, where we put all those devices in this particular fashion, where the line cards become leaves and the fabric card becomes spines. And if you look at the disaggregated schedule fabric, there's something that we have done with one of our customers, where we have built an 18K GPU zones, L1 zone of 4.5K, and an L2 AI zone for 18K GPUs, and that could interconnect across multiple zones, where to go all the way up to 32K GPU scale. The limitation of DSF is your scale ceiling is at 32K GPUs. The reason why it is a 32K GPU is because of the number of VOQs that a system supports. It is also a proprietary fabric. That means I cannot have a cell base and a packet base interoperate in this kind of a network. Either it has to be a cell based or it has to be packet based. And there is a little bit of induced latency because of the way you build your fabric with your fixed systems. And there's a lot of cost and operational overhead in running this kind of a network. And then you have to improve those beyond this particular thing. We essentially defined another set of network called a non-scheduled fabric. It is essentially more of a class topology where it employs packet spraying capabilities. When I say packet spraying capability or adaptive routing capabilities that you see with a lot of hype from NVIDIA and other places, where you spray the packets across this part of the network, and on the egress side of things, the NIC essentially does the reassembly of it. So the packets can come out of order, and this will actually gives you the best load balancing of all the stuff that we have talked about so far. From that, now we are evolving to these scale up, scale out, and scale across topologies in the future, where from a scale up point of view, we are trying to build the biggest, largest memory fabric with GPUs. An example of that is the NVL72 from NVIDIA, from a scalar fabric point of view. This is essentially predominantly used for AI inference. No problem. Continue? Or I don't know whether I want to continue or not. All right. Have another 15 minutes or so. So continuing on actually from an evolution point of view, what you will see in the next few years, people talking about scale up, scale out and scale across. Scale up essentially is you're trying to build a biggest memory fabric similar to NVL72. Then if you really wanted to connect multiple scale up racks, what you have to do is now to have to build something called a scale out on top of that. The scale out domain essentially which is less than 2 kilometers apart. Hello? Hello? Then now if you really wanted to connect across data centers, for here an example which is a San Jose to Bakersfield, which is 400 kilometers or so, you have to have another layer on top, what we call it a scale across. Scale across typically deploys high buffered switches. Because for latency and buffer management. These are some of the future looking physical challenges that you would see. Now, if you look at a typical GPU rack, the GPU rack is easily exceeding 100 kilowatts. The chips that are actually currently in place the chips that are actually there today are exceeding 1000 watts or so, whether it is a GPU or whether it is an NPU ASIC. The cooling capacities that are there today that you have to run your fans at higher speeds, the cooling capacity is getting exhausted. You cannot contain the hot aisle in your data center environment. you do not have a proper load bearing and water loop facilities. And the power delivery at the rack bus bar is actually reaching its limit. Another problem that you see is the bandwidth and optical density. The faceplate bandwidth is going beyond 800 gig, 1.16, 3.2T in the future. The pluggable optics power budget is incrementally increasing. The PCB trace losses at the SerDes beyond 200 gigins per second reach, seeing a lot of trace losses. The front panel cable management density is becoming harder and harder to deploy. Signal integrity and retimer overhead is another challenge. And optical links power contributing system power growth. Those are some of the future-looking physical challenges that we have, and we're trying to solve them. And one of the ways you solve is through concept called liquid cooling. So today, historically, when you say look at an IT rack power trend from 2000 to 2025, you would see that the rack power increases 1 kilowatt per year rate. The highest density racks we have seen is 25 kilowatts. From 2020 onwards, the rack power density grew at 10 kilowatts per year rate. That means you have a 3x power demand increase with every CPU, GPU generation, starting with H100. So the customers have to make a decision, where do you tip from air to liquid cooled? Airflow, obviously, as you guys know, is a non-linear to fan power. 50 kilowatt is practical and economic limit. The moment you go beyond 50 kilowatt on your system, you have to think liquid cooling. That is where liquid cooling comes into picture. A liquid cooling capabilities have 3 different functions. One is you have a facility water, which you typically call it as a primary loop or a coolant. Then you have a technical water, which is a secondary loop, which has deionized water or propylene glycomax. And there is a CDU in the middle, which does liquid to liquid heat exchanger. So these loops never mix at all. So why do you use PG35? Why can't you use DI water? DI water actually looks over for ions, and they can cause corrosion into the system. They cannot handle boiling temperatures beyond 100 degrees centigrade. The water freezes below a certain temperatures. For all of those things, we need to use this 25% PGL mix for your liquid cooling stuff. Some of the things that we are essentially doing for improving the signal integrity and power reduction on your optics module, one of the biggest contributor for your systems right now is your optics. So when you take a look at an optics or a pluggable optics module, what you see is an optic module would have a DSP or an optical engine in its stuff. That's where it's connected to your front panel ports. And you have a PCB, through PCB traces connects to your NPU ASIC. That is how pluggable optics works. Now, when you go to 200 SerDes and 400 SerDes, it's really hard to put up a retimer optic. The amount of power that is consumed is high. So what you do is, you essentially now, you're moving away your optical engines, packaging it with your NPU ASIC itself, which is why it's called a co-packaged optic. So that the distance between your optics module or the OE and the NPU ASIC is reduced to millimeters. This will improve signal integrity, reduce PCB trace loss, gives you less power and things like that. There are other ways you can actually reduce the power of your retimed optics. One, retimed optics essentially is something where you have a DSP both for the TX as well as the RX that consumes the maximum amount of power which you need for signal integrity, maintaining the integrity of the signal, making sure the signal strength is good, making sure the equalization is there. Now the other aspects that you can actually do is you can do something called a half retimed optics. When I say half retimed optics, that means you would have DSP taken away on one side of your optic. So the other side is essentially driven by the NPO. The non-retimed optics or the LPO is where the DSP does not, the optics does not have a DSP at all. All the TX and the RX functions has to be done, all the modulation has to be done by your NPO itself. So if you go the LPO route or half-time route, you're essentially saving somewhere between 60% or so of your optics power. These are really powerful stuff, and we are working closely with a lot of transport and system architecture vendors, whether it is UEC, Ethernet Alliance, Open Compute platforms to improve or solve some of the challenges that we have seen in our previous slides, and also working towards accelerated interconnector landscapes. We're focusing on how do we solve some of those interconnect issues that we have in place, whether it is UCI for intra-package, ESN for internode, CXL and UALink for intranode capabilities. And then finally, this is where we are in the future. We might go 3 use cases for quantum technology ecosystem. One is computing, networking, and quantum sensing. We are actually focusing more on quantum networking. We're focusing more on quantum networking. There are a lot of use cases that are essentially coming in terms of quantum applications. It could be drug design, forecasting, weather forecasting, computational forecasting, logistics, optimization. Cryptography is another big thing that is being in the works right now, and probably that's going to be the first application that you would actually solve for with quantum is cryptography. And that's pretty much it for my slides, and I just want to thank you again for this opportunity to present.
Tell in 3 lines what you are trying to tell. We are not able to hear properly.
I understood his focus has been for the new era of artificial intelligence, when you are going to have lots of GPUs which are going to do the functions for the AI, require high power requirements. So he told us how to do different kinds of cooling systems, how to reduce the power requirement using photonics, optical systems and things like that, and right from device to the computer, to the chip and to the board, and also different kinds of cooling devices. That is what I heard in the last 3, 4, 10 minutes. Before that I do not.
Thank you so much for your amazing lecture, sir. And we apologize for a little lapse in between. Thank you so much. That was very enriching. As a token of gratitude for your wonderful, excellent presentation, we would like you to felicitate with a memento. May I request all our audience to put your hands together. Thank you, sir. Thank you so much. And now, it's time to launch the official song of Stanley College of Engineering and Technology for Women. I'm sure it's going to definitely be liked by all our audience here today, and I'm sure you'll like it very much. Let's listen to Stanley's anthem. That is a song that is actually done for today's reveal.
సప్తస్వరాల సరిగమల స్టాన్లీ సప్తవర్ణాల వెలుగుల స్టాన్లీ జ్ఞానదీపం వెలిగించే స్టాన్లీ జ్ఞానదంగా ప్రవహించే స్టాన్లీ జయ హే या वैभवपूर्तिविरूपम् सारे जहां से अच्छा स्टैनली हमारा जय हे स्टैनली जय जय हे तेलंगाना सप्तस्वराला सरिगमल स्टैनली सप्तवर्णाల వెలుగుల స్టైలీ జ్ఞానదీపం వెలిగించే స్టైలీ జయ హే స్టైలీ జయ జయ హే స్టైలీ సప్తస్వరాల సరిగమ
I'm sure the song is very soulful and a wonderful rendition. I definitely thank our Dr. Rajesh sir from Department of ECE for the vocals and for such wonderful rendition. We thank the singer too. And now we are ready because I know that here for us today I'm sure the ladies and gentlemen here, the atmosphere in Chitamber Hall is absolutely electric because we've seen that our esteemed luminaries, stalwarts of academia, and titans of defense research are already in the in our hall right now. So I would like to definitely take this moment to formally welcome all our dignitaries, delegates, and guests for a truly historic evening ahead. I'm sure you all are with me. Are you all? Thank you so much for that.
Now, it's our absolute privilege to invite all the highly distinguished guests to grace the dais. We proudly invite onto the dais Dr. B.L. Raju, Principal, Stanley College of Engineering and Technology for Women. Put your hands together. Professor Prabhu G. Benakop, Principal, Methodist College of Engineering and Technology. Shri K. Krishnarao Garu, Secretary and Correspondent, Stanley College of Engineering and Technology for Women and Methodist College of Engineering and Technology. Please put your hands together.
And now we respectfully invite Shri MGPL Narayan Garu, Chairman, IEEE Hyderabad section, onto the dais. Please put your hand together for our respected dignitaries. And then Dr. S.K. Chowdhury Garu, Retired Director, RCI, DRDO, and Vikram Sarabhai Awardee and Conference Advisor ICESAIS. Please put your hands together in welcoming Dr. S.K. Chaudhary Garu. And now, another conference advisor who made this conference happen for us, Dr. B.H.V.S. Narayanamurthy Garu, VC Diet Pune, and conference advisor.
Next, we welcome our revered guest of honor, Dr. Jagannath Nayak, Distinguished Scientist and Director General, Missiles and Strategic Systems, DRDO. Shri Raja Babu, Distinguished Scientist, former Director General, Missile and Strategic Systems, DRDO. Shri Anindya Biswas, Distinguished Scientist and Director, RCI.
And finally, we invite the leaders of tonight's program. The president of the program, please put your hands together for Professor Kumar Mulgaram Garu, Vice Chancellor, Usmania University. Kindly welcome with a great applause. And our esteemed chief guest, Dr. V. Saraswat Garu, member, Niti Aayog. Please put your hands together in welcoming them. We would request Shri Rakesh Reddy Garu to be on the dais. Please put your hands together. We have a galaxy of luminaries here today on the dais, and there is no other way to really invite them other than really giving a floral tribute. May I request all our head of the departments to definitely give our luminaries a floral tribute. Please put your hands together, everybody. Let the hall be electric. Stanley Women Power. Thank you so much. I thank all the HODs for their wonderful tribute. And I thank all our luminaries for their time today. Give me a moment.
Shri MGPL Narayana Garu, Chairman, IEEE, and Dr. is unable to come, so he expressed to convey best wishes to the conference proceedings and conference. Now, to invoke blessings and mark the formal commencement of the inaugural session, we request our chief guest and other dignitaries to kindly light the lamp. Lighting of the lamp. दीपम ज्योति परब्रह्म दीपम ज्योति जनार्दन दीपो में हरतु पापम संध्या दीपो नमोस्तुते. I bow to this sacred lamp, the symbol of auspiciousness, prosperity, health and wisdom. May this divine flame dispel ignorance, remove negativity and illuminate our paths with the light of supreme truths.
As the light dispels darkness, may it pave the way for innovation and endless learning over the course of ICESAIS 2026. Thank you, dignitaries. Now let us all stand in deep reverence for the national song Vande Mataram. May I request everybody in the hall to stand up?
वन्दे मातरम् वन्दे मातरम् सुजलां सुफलां मलयज शीतलां सस्यश्यामलां मातरं वन्दे मातरम् वन्दे शुभ्रज्योत्स्ना पुलकितयामिनी पुल्लकुसुमित रुमधनशोभिनी सुहासिनी सुमधुरभाषिणी सुखदां वरदां मातरं वन्दे वन्दे मातरम् कोटि कोटि कण्ठ कलकल निनाद कराले कोटि कोटि भुजे धृत कर करवाले अबला के नोमा ये तो बने बहुबलधारिणी नमामि तारिणीं रिपुदलवारिणीं मातरं वन्दे मातरं वन्दे मातरम् तुमि विद्या तुमि धर्मा तुमि हृदि तुमि मर्मा तुम ही प्राणाः शरीरे बाहुति तुमि मा शक्ति हृदये तुमि मा भक्ति तोमराय प्रतिमा गढ़ि मंदिरे मंदिरे वन्दे मातरम् वन्दे मातरम् कलशप्रहरणधारिणी कमला कमलदला विहारिणी वाणी विद्यादायिनी नमामि त्वां नमामि कमलाम् अमलाम् अतुलां सुजलां सुफलां मातरं वन्दे मातरं वन्दे मातरम् श्यामलां सरलां सुष्मितां भूषितां धरणीं धरणीं मातरं वन्दे मातरं वन्दे मातरं वन्दे मातरं
Thank you all. Please be seated. To welcome the formal welcome address, it's our honor to introduce the General Chair of ICESAIS, Dr. B.L. Raju. Dr. Raju is an eminent academic leader and dynamic principal of Stanley College. With the decades of profound contributions to engineering, education, and research mentorship, his visionary leadership is the foundational pillar to bring this global standard conference to life today. Ladies and gentlemen, please welcome Dr. B.L. Raju.
A very good evening to one and all. Respected Chief Guest, Dr. V.K. Saraswat Sir, Padma Bhushan, Member Niti Ayog, Government of India. Respected President of the Program, Senior Professor Kumar Molugaram Sir, Honorable Vice Chancellor, Usmania University. Respected Secretary and Correspondent, Sri Krishna Rao Sir, Secretary and Correspondent of Stanley and Methodist. And also he is the member of the court, Manipur Central University. Respected guests of honor, Dr. Jagannath Nayak Sir, Director General of Missiles, DRDO, Dr. Rajababu Sir, former Director General of Missiles, DRDO, Sri Anindya Vishwas Sir, Director RCI, DRDO, Sri MGPL Narayana Sir, Chairman IEEE Hyderabad Section, Dr. S.K. Chaudhary Sir, former Director RCI, DRDO, Vikram Sarabhai Awardee, FNAE, Senior Life Member, IEEE Conference Advisor. Professor Prabhu Bankap Sir, Principal Methodist College of Engineering and Technology and General Chair. Heads and members of committees, coordinators, distinguished guests, keynote speakers, eminent academicians, scientists, researchers, industry leaders, delegates, faculty members, dear students, ladies and gentlemen, a very good evening to one and all. It is my immense pleasure and privilege to extend a warm and heartfelt welcome to each one of you to the inaugural ceremony of International Conference on Electronic Systems and Artificial Intelligence Applications. Today we are truly privileged to witness the presence of some of the finest scientific minds, visionary academicians, technology leaders, and policy makers of our nation. Your gracious presence has elevated this occasion into a truly distinguished gathering of excellence. On behalf of Stanley and Methodist, and the entire organizing committee, I extend our sincere gratitude for accepting our invitation despite your demanding schedules. Your presence today symbolizes the strong partnership between academia, research laboratories, industry, professional bodies, and national institutions. A partnership indispensable for building an innovation-driven, technologically empowered, and self-reliant India. Before I conclude my welcome address, allow me to briefly present the two institutions that have joined together to host this prestigious international conference. Now about Stanley College of Engineering and Technology for Women. Our college has been dedicated to empowering women through quality engineering education for over 2 decades. Today, the institution proudly stands as a UGC autonomous institution with all eligible undergraduate programs accredited by NBA under prestigious Tier 1 format, reflecting the highest standards of engineering education. The institution is NAC-A accredited and has been consistently recognized among the top 10 engineering colleges in Telangana and top 100 engineering colleges in India as per Times Engineering ranking. Stanley has built a strong ecosystem for research and innovation, securing more than 3 crores of grant for research and also for consultancy, publishing 592 Scopus indexed research publications and contributing over 90 patents to prepare students for the technologies of tomorrow. The college has established centers of excellence in artificial intelligence, data science, and Internet of Things. More than 1/3 of our faculty members holds PhD degree, creating a vibrant academic and research environment. Our students have consistently brought laurels through state and national level hackathons, innovation challenges, technical competitions, and extracurricular achievements, reflecting the trust reposed by students and parents. Stanley has emerged as the third most preferred engineering college under Usmania University based on the latest TG EPSET rankings. About Methodist College of Engineering and Technology. Our esteemed partner institution, Methodist, has carved a niche for itself through academic excellence, innovation, and research. Methodist is a UGC autonomous accredited with prestigious NAC A+ grades with NBA accreditation for 5 undergraduate programs, and it is recognized by Usmania University as the research center for offering PhD programs in mechanical engineering. The institution has created an outstanding innovation ecosystem through its IICT Idea Lab, established with a grant of 90 lakhs, along with centers of excellence in data science and Internet of Things, and the IMEDA Technology Business Incubator, promoting entrepreneurship, technology-driven innovation. Nearly 45% of its faculty members hold PhD degrees, providing exceptional academic leadership and research mentorship. The institution has made remarkable contributions to research through funded projects, consultancy, and intellectual property, with 165 patent filings, including 140 published, 25 granted patents. Methodist also enjoys strong collaborations with premier academic institutions, leading research organizations, and globally renowned industries, providing students with exceptional opportunities for learning, research, innovation, and career advancement. Together, Stanley and Methodist are united by a common vision to nurture competent engineers, promote impactful research, foster innovation, and contribute meaningfully to the national development. Yes, IEEE Hyderabad section and every participant who has travelled from different parts of India and abroad to be with us today, I wish all of you an intellectually enriching, professionally rewarding, and memorable experience. Thank you very much.
Thank you very much, sir, for the exceptionally warm welcome and setting truly grand and inspiring vision for the conference. Thank you.
And now let me take this opportunity to introduce to you all Professor Chatterjee. ICESAIS 2026. Sir is an academic leader and distinguished principal for 35 years, and sir has won so many prestigious awards. Sir has so many scholars that he's actually guiding that, and I'm sure behind this conference there are two people. One is the principal of SETW and the other is Methodist College.
Good evening to all the distinguished delegates, eminent dignitaries, respected academicians, scientists, industry leaders, researchers, faculty members, research scholars, and members of the media. It is indeed a great honor and privilege to welcome you all to the International Conference on Electronic Systems and Artificial Intelligence Applications, and take this opportunity to present a brief overview of this international conference. This conference is jointly organized by the Avionics Society of India, Methodist College of Engineering and Technology, and Stanley College of Engineering and Technology for Women, with a technical co-sponsorship of IEEE Hyderabad section, and also sponsored by Computer Society of India, and industry sponsors are Qualcomm, Anant Tech, Air Force, Accutronic, and Electro Circuit Systems. We are deeply honored by the gracious presence of our Chief Guest, Dr. V.K. Saraswat, Padma Bhushan awardee and member Niti Aayog, Government of India, whose visionary leadership and remarkable contributions to India's strategic and technological development continue to inspire generation of scientists and engineers. We are equally privileged to have Senior Professor Kumar M., Honorable Vice Chancellor of Osmania University, as the President of this function. I also extend a warm welcome to our distinguished dignitaries, Sri Raja Babu Sir, former Director General of Missiles, DRDO, Sri MGPL Narayana Sir, Chairman IEEE Hyderabad Section, Dr. S.K. Chaudhary, former Director RCI, DRDO and Vikram Sarabhai Award, Sri K. Krishna Rao Sir, Secretary and Correspondent, Methodist College of Engineering and Technology and Stanley College of Engineering Technology, Sri T. Rakesh Reddy, Director Infrastructure, Professor B.L. Raju, Principal, Stanley College of Engineering and Technology, Deans and Directors, Head of the departments and delegates from different parts of India and abroad, and scientists from NSTL, ISL, DLRL and RCI labs. Once again, I extend a very warm welcome to each one of you. The theme of this conference covers artificial intelligence and electronic systems, and which is transforming every stage of human life, from healthcare, transportation, communication, manufacturing and smart cities to aerospace, defense and national security. With this vision, this conference has been considered as a premier international platform to promote knowledge sharing, resource, encouraging interdisciplinary skills and research and innovation in the AI related fields as well as core branch of engineering. During the next 2 days, the conference will feature keynote lectures, invited talks and parallel technical sessions covering emerging areas such as AI, machine learning, deep learning, embedded systems, VLSI design, signal processing, IoT, cyber security, robotics, quantum computing, smart systems, renewable energy technologies, electric vehicles and all. I am delighted to share that conference has received an overwhelming response from the global research community, that we have received 1593 paper submissions, including 48 international submissions. After preliminary screening, 1559 manuscripts processed to the formal peer review stage, and review process was conducted through the Microsoft CMT platform using rigorous double-blind peer review system. 458 reviewers were invited, 320 accepted for invitation, and 282 expert reviewers successfully completed 3,118 independent reviews. Based on these evaluations and stringent quality standards, 162 papers were accepted for presentation, resulting in an acceptance ratio rate of 10.4%, reflecting the high academic standards of the conference. One of the unique highlights of this conference is pre-conference workshops organized this morning, featuring 3 specialized tracks on AI and IoT emerging technologies, drones and anti-drone systems. Experts from DRDO, Qualcomm, HELX, Aeroforge Labs and other leading organizations delivered insightful sessions and hands-on demonstrations, successfully bridging the gap between academia, research and industrial applications. The enthusiastic participants from universities, premier research laboratories, industries, startups and government organizations reflects the growing importance of interdisciplinary collaboration in solving the real world problems. At this juncture, I express my sincere gratitude to IEEE Hyderabad section for its valuable technical co-sponsorship and Avionics Society of India for its constant guidance and support. Our distinguished keynote speakers, reviewers, session chairs, CSI, industry sponsors Qualcomm, Anant Tech, Air Force, Accutronic, Electro Circuit Systems, organizing committees, faculty members, administrative staff, and our enthusiastic student volunteers. Their dedication, commitment, and tireless efforts have made this conference a reality. Our delegates, dear delegates, I encourage each one of you to actively participate in the technical sessions, interact with your fellow researchers, exchange ideas, and make the most of this exceptional opportunity for learning, networking, and collaboration. I once again extend my heartfelt welcome to all of you to Hyderabad, a city known for its rich heritage, vibrant culture, and rapidly growing technology ecosystem. I wish you an intellectually stimulating, professionally rewarding, and memorable experience at this conference 2026. Thank you, and I wish you the conference every success. Thank you.
Am I audible right now to everybody? Right. Thank you so much, sir. So we have tried to really put it very succinct when it comes to your profile. Excuse us if they extend for a while because you have so many milestones. May I now go ahead with our next speaker. We now introduce our guest of honor, Shri Raja Babu Garu. Sir is a leading figure in Indian aerospace defense with a distinguished 35-year career spanning the Indian Air Force and DRDO. Sir pioneered the design and successful demonstration of India's ballistic missile defense system as a program director for Mission Shakti. Please put your hands together. He led the historic demonstration of India's first ever anti-satellite missile test and revolutionized advanced missile avionics as director of RCI. And please put your hands together, a recipient of the Agni Award for Self-Reliance and DRDO Scientist of the Year. Sir, thank you for coming with us.
Dr. V.K. Saraswat, Chief Guest for today's function. Professor Kumar Maulagram, Vice Chancellor, Usmania University. I think I'll use this. Distinguished guests on the dais and off the dais, and dear students, first my compliments to Stanley College of Engineering and Methodist College of Engineering and IEEE for organizing this conference on the topic of relevance today, that is both on electronics and applications of AI. I am sure for the students it makes a great difference, because our generations we saw progression of electronics starting from transistors, then microprocessors, semiconductors, and we saw the evolution as the sizes became smaller and smaller, with the processing powers becoming manifold. But I think now is the time that we bring in artificial intelligence also along with electronics, so that the both together, electronics and artificial intelligence, they redefine the living of the mankind. You all are aware how AI has made so much of difference in the past few years. Now the day has come that the intelligence of the machines is almost overtaken the humans. Today we found many applications where there are applications which mimic humans. Today with the evolution of sensors, there are many sensors which replicate human organs, and with the thinking of humans we find that many applications we feel as if humans are undertaking those tasks. I think day before yesterday I was reading a news article where the robots have carried out surgery on humans, and today we find many applications where driverless taxis are going on the roads. In fact, it was brought out that the sensory outputs are so good that probably the driving skills are even better than humans, because everything is programmed, there is no scope for errors. So this is the progression of artificial intelligences, and as we move on, more and more such applications will come. So it is a challenge for your generation. How we are going to compete with this artificial intelligence is always, the race between, human intelligence and artificial intelligence, especially with evolution of quantum computing and all, where the processing power is going to increase many-fold, and the intelligence algorithms and the way they are being processed at such a speed. So it's always a challenge between humans and then machines. So it is a challenge for your generation, how you are going to cope up in this area of artificial intelligence. And I think the 3-day seminar which is organized by both the institutions and IEEE are very relevant for today. That is for both the progression of electronics and then artificial intelligence, and how together they are going to redefine the technology in the future. I don't want to take much time. We have very, very interesting talks ahead, and I wish the 3 days of seminar is going to be a great success, and you all get many bright ideas which you can probably practice in the future and see and contribute to the growth of technology. I thank everyone for giving me this opportunity. Thank you.
Thank you so much, sir.
Moving on to our next speaker, Shri MGPL Narayana is a distinguished tech leader and global volunteer, currently serving as the section chair for the IEEE Hyderabad section. He brings decades of deep expertise from his time as the vice president and the chief scientist at Tata Consultancy Services. He also drives international engineering standards as the deputy chair for DIITA under the IEEE Standards Association. Over to you, sir.
I thought 5. Make it 2. Good evening. Respected Dr. V.K. Saraswat, Padma Bhushan and chief guest, Professor Kumar Molgaram, president of the program, VC OU, distinguished leaders from DRDO, Avionics Society of India, Academia and Industry, Mr. Krishna Rao Garu, who is the secretary and correspondent of Stanley and the other college, and Dr. S.K. Chaudhary Garu, who is the, his conference advisor, and I met him, but he's a very active person, I should say. And Professor Prabhu Benakoff, Professor B.L. Raj Garu, distinguished speakers, researchers, authors, and ladies and gentlemen. Good evening to all of you. It is my privilege to represent the IEEE Hyderabad section at the inauguration of the 2026 International Conference on Electronic Systems and Artificial Intelligence Applications. On behalf of the IEEE Hyderabad section, I extend my congratulations to the organizing institutions, Methodist College of Engineering and Technology, Stanley College of Engineering and Technology for Women, and the Avionics Society of India for bringing together an impressive gathering of researchers, academicians, industry professionals, and technology leaders. The theme of the conference is both timely and significant. We are living in an era where artificial intelligence is converging with electronic systems, embedded intelligence, communications, sensors, robotics, autonomous systems, and semiconductors. These technologies are no longer evolving independently. They are collectively shaping the future of the industry, defense, healthcare, mobility, manufacturing, and society. This makes conference like ICESAIS particularly important. They are not merely venues for presenting research papers. They are platforms where ideas are challenged, collaborations are formed, and innovations begin their journey from laboratories to real-world applications. IEEE is pleased to technically co-sponsor this conference. Technical co-sponsor is much more than the use of IEEE name or logo. It represents a shared commitment to technical excellence, rigorous peer review, research integrity, ethical publication practice, and dissemination of high-quality knowledge. Over the last few months, the IEEE Hyderabad section has been working closely with the conference organizers across the section to strengthen this conference ecosystem. I am delighted to see the ICESAIS brings together an outstanding combination of academia, industry, and learning, leading national research organizations such as DRDO. This is precisely the kind of collaboration that IEEE seek to foster. Many of the grand challenges before us, from trustworthy AI to resilient electronic systems and intelligent autonomous platforms, cannot be solved in isolation. They demand interdisciplinary research, industry engagement, and sustained collaboration. To the young researchers and students who are present here, I would like to say this: do not measure the success of your research merely by the number of papers you publish. Measure it by the problems you solve, the collaborations you build, the technologies you influence, and the positive impact you create for society. IEEE provides a global platform not only for publishing research, but also for participating in standard development, professional networking, and entrepreneurship, lifelong learning, and technology for humanity. I encourage you to take full advantage of these opportunities. Particularly the idea of standard development is very important, particularly with the advent of the AI. Unless we have the standard to deal with the AI, we are doomed. In fact, I am also looking after IEEE standard in the area of DITA, that means dignity, identity, inclusion, trust, and agency when you deal with the autonomous systems, including the AI. So conducted a program in the month of May, good response. So it is beyond technology. It is dealing how the humanness you have to incorporate in the systems that you build. I once again congratulate the organizers for their vision and commitment in bringing together this distinguished conference. On behalf of IEEE Hyderabad section, I wish ICESAIS 2026 every success. May the discussions over the next 2 days inspire new ideas, new partnerships, and innovations that advance technology for the benefit of humanity, which is the mission statement of IEEE. Thank you all, and I wish you all very successful conference. Thank you very much.
Thank you very much, sir, for highlighting the continuous support and standard of excellence set by the IEEE Hyderabad section.
I take this quick introduction to our conference advisor, Dr. S.K. Chaudhary Garu, former director of RCI DRDO, and a prestigious Vikram Sarabhai Awardee. Please put your hands together. And sir has been a fellow of the Indian National Academy of Engineering and a senior life member of IEEE. And sir is widely recognized for epoch-making contributions of space and defense systems engineering. We welcome you, sir.
I wanted to, is it audible? I wanted to make it as short as possible because your principals made me to force, but Dr. Saraswat wants to hear. Sometimes we have to communicate to him and we have to get some hearing from him. Both the things are required. So what he always asks me, what for you are doing there? See, I thought it is my duty after retirement, when I'm doing for so many startups, why not keep the startups bindingly with some college? So as a first step, I started doing in Andhra Pradesh, where it is already working, where Chandramanu Naidu has supported that, a great center has been made. And Bharat Force is supporting for outside. Central University, Anandpur is in Noida. Why Central University? Central University can get funds from abroad. And their first approach, I have seen there and gone, data center, anytime President visited last week. Nothing better than that. Then what is the next one? A studio. Then the connectivity. As today, Suman was telling, I wish Saraswat should have been there, Suman's presentation. He says, what is AI? And what is cutting edge of AI very nicely. So that has to be done here also. In the hub or the center, that has to be done. Whatever I am doing here, it should go to the other college. I want IEEE also to get some funding. I'll help you to write your things. Already, that FNA group, I've told them, they are in that. And Saraswati, if he supports, will get more. Okay, that is my main aim, because workforce is not there. Most of the scientists you are seeing, EFG, A, B, C, D are missing. So how to get over that? That's why today morning session was very important for me. Anybody says morning session is bad, tell me. I got from all the sections. And I have put my youngest scientist, Mr. Satrana, to give lead for this thing. Luckily, he started his career from hardware in loop simulation. My own daughter, they forced. So that way, Madhumita was very helpful, and our Lalit Shankar also worked a lot, and obviously, my main man is Prakash. Raju, you stand here. He is really a professor come scientist. He is basically, nobody knows, all strategic system, control system design is Raju. Control system design of strategy. I am very much in frequency with him. Myself and Kadam, we are the great friends of him. So with all this gathering, and Sam Chetty, whenever I call, he'll come. We are friends. Saraswati, you may not know, we have started from hinge moment with him. That is our relation. And then all the aerodynamics uncertainty, including the LCA, they have never left me. I was always there with him, and Subramanian was there, but Sam Chetty Subramanian knows we are friends. And finally he became the NL director. And today, Dr. Kalam used to call me white man's friend. I was called white man's friend. He called me back. This fellow was told, if he comes here, goes to Bangalore, he'll never come back. He gave me a letter. Only Kalam has given that letter to me. Exigency of service, you cannot be released. I can show that to anybody. And must be behind, he is there. He must be doing that thing, I have to tell them. Anyway, I have grown. He has allowed me to set up the Hills laboratory, where all of the things we have put. We have put the state-of-the-art processors working. We want to continue that knowledge. But today, I am finding the people between the age of 45 to 60, they are mostly in Delhi. How they will teach them? That is the question I asked Satish. Satish was very answer me. Are you understanding? If there is no leader, then I have to get Chitamber. He is better. Are you understanding? That's what I'm telling you. That somebody has to be in between. So you take another young force with some good projects, at least do certain portion of the world. What Satyana was talking in the morning, multiple intelligent AI around, with multiple AI. And Dr. Saraswat no Srinivas, stand out. We have already implemented AI for your project. Okay? So it is not we are going back. And I have shown to Kadam also, that one, what I am doing. So that has been implemented, but we have to go further. With Satyana, it will become better. Okay? Something new has come. I want to give that. We all follow Shannon theorem. Shannon theorem is the signal, the way it is fluctuating, our signal should be 5-10 times more than that, so that we don't miss any peaks. Satyana is now challenging me. He has made with less also can do. Some technique of AI. I have gone through something, but it is impressive. We will try to improve it. Then today, some more fuel has been given by my daughter. She has told many things. You have heard how to multiply, and he has given practical data. So in this college, with the environment of, here is one gentleman, he is already doing a lot of IT and all. Jaishankar is always a disciplined man. Another fellow, Karthik. Karthik has given fantastic support. Fantastic support. Obviously, Bhava should not get angry. And all the time, our Raju Sahib will make things okay. Whenever I need power, Prabhu has given. Power is been given by Prabhu. This is the way we have distributed the work. And I am not told the main man who has helped me maximum is Raja Babu. Raja Babu has continuously told me, no problem, sir. And both the directors, Anindya Vishwas and all, they have not come here, but they have given fantastic support. I have called people who have given support. He and Anindya Vishwas contributed. Even the ASL director, he is coming there. He is a genuine person, he is a promotion person. He is very good here. And hello, Kanti Rekha, new PD. Hello, what is the new PD? Kanti Rekha is my hills man from Agni side. Kanti Rekha is always with us. I cannot forget Kanti Rekha's contribution. I have got your RCI child. He has talked to Sarsad already, who is making the drone. So I have tried to support. Aim is to get build up of a center of excellence. This is very important, sir. Vice Chancellor. Center of excellence, not again bhashan, not papers alone. Center of excellence combined with Maker's Place. Maker's Place. Now Maker's Place, prototype. I am not asking. I have told for the students, Center of Excellence and Maker's Place. We called it COE and MP. That is, you don't chase me. And that one has to be done. But Maker's Place cannot be done without the support of some big shots. I want to tell, I got the support from Bharat Force. Dr. Saraswat knows very well. They have paid 10.5 crore to Basha with the aim of setting up a laboratory there. Now, that is operational and full support of Central University as a co-planner. They are also extremely good. So like that, it should grow here. So I am attempting one, and he will again curse me. I am trying one more in Jadavpur. Jadavpur, the Vice Chancellor is a Kanpur IIT man. So he is trying something. So here Sopan Gopal is there. He will say, he will help me. Okay? Lot of Jadavpurians are there. Okay? So I want to finish this because I want to hear his lecture. So please bear with it. Otherwise he'll fill up quickly. Messi, you have heard me? No? Anything? Okay, bye.
Thank you so much, sir, for setting such a powerful tone for this conference. And now, I take this immense pleasure and honor to introduce our esteemed leader, Senior Professor Kumar Murugaram, sir, the 26th Vice Chancellor of Osmania University. I'm sure we all know that sir is an eminent academician, distinguished researcher, and visionary administrator. Sir has
over 300 research papers and secured UGC and DST SERV funded projects and guided numerous ME dissertations and PhD scholars and established the ME Transportation Engineering program at Osmania University. And for his outstanding contributions, Sir has been recognized with the State Meritorious Teacher Award. Please put your hands together. And the Engineer Award in 2018. Internationally acclaimed, he has represented Osmania University in over 15 countries, participated in the prestigious MHRD LEAP program, and continues to contribute to national infrastructure development as the State Technical Agency for PMGSY roads in Telangana and Andhra Pradesh. And now, ladies and gentlemen, to share his vision on innovation, leadership, and the road ahead, please join me in welcoming on the stage a stellar educator, reformer, and a pioneer, Senior Professor Kumal Molugaram, sir, to share his presidential. Please let the hall ring in with your applause.
Very good evening to one and all. All the dignitaries on the stage and off the stage, the faculty members, and the scientists from DRDO, and the researchers, and dear students. It is indeed a privilege and honor to stand before you in this inauguration of International Conference on Electronic Systems and Artificial Intelligence Applications. I congratulate the Methodist College of Engineering and Stanley College of Engineering for Women for floating such a wonderful program in association with IEEE and Avionics Society of India for organizing this prestigious conference for the sake of stakeholders, researchers. I appreciate my heartfelt appreciations to all the organizers for bringing together eminent personalities, scientists, policymakers, and industry leaders, and young researchers on a common platform to share various developments taking place in the research on the floated topic. The era of artificial intelligence, it's a catchy word. From 3 years small child to 90 years old gentleman, everyone talking about artificial intelligence. This artificial intelligence is no longer a technology of the future. It is the transforming every aspect of our life today. AI coupled with advanced electronic systems is revolutionizing healthcare, agriculture, education, transportation, defense, manufacturing sector, and governance. Every aspect and everywhere we are using artificial intelligence. The India's vision of becoming a global technology leader depends on significantly on innovations and emerging from situations like ours. If you look at the technological transformation since the last 30 years, the mobile revolution is an abnormal kind of, the revolution because of the microwave technology, because of networking, and a lot of transformation because of mobile. Everything made very simple, and further smoothening also required, further refinement also required, only with the objective that any technology that should reach to the non-reachable. The main objective is any technology, whatever we focus, the technology should be reachable to the non-reachable and affordable. With this objective, every scientist, every innovator should work on these guidelines. And the second one is solving unsolved problems of the society. There are so many problems in the society. And if you look at the recent apps, many apps helping a lot to the society, simplifying the things. There is a lot of potentiality by the youngsters to invent or to help the society by solving unsolved problems of the society in all fields, not only engineering. I don't want to take much time because already a lot of time consumed, but I want to focus on few things. No doubt India's vision. India is progressing rapidly towards becoming a knowledge-driven and technology-powered nation. Initiate such a Digital India, Make in India, Startup India, Made in India, and the National Education Policy 2020 have created unprecedented opportunities for innovation and entrepreneurship. The wide opportunities are open. The potentiality of getting, the job, potentiality of getting entrepreneur is increasing today because of these reforms. The future belongs to those who can integrate artificial intelligence with human values for sustainable development. And if you look at the Vikasit Bharat concept 2047, Bharat should become developed country by 2047 with $30 trillion economy. So this is possible with the only education, quality education and skill-based education. Only this is possible. Therefore, we have to focus on quality education, skill-based education, quality research, and quality innovation and patents. One should focus on patents also. If you look at the developed countries and our country, we are little backward in the the patents, even filing and getting and granting of patents. And potentiality for India is our youth. So less than 30 years age, almost 60% of the youth available. And at the same time, less than 25, the 50% of the youth is available. If you make the youth and shape the youth in a proper way, definitely we will achieve the Vikasit Bharat concept, the 2047 India will definitely become, developed country. And at the same time, if you look at Telangana definitely will become number 1 by 2047 because of various policies and reforms, reforms coming in Telangana. So because of that, with the 3 trillion economy, intended economy by 2047, the Telangana also will become number 1. Lot of potentiality is there in various sectors. So the opportunities are plenty, and therefore the students and research, they have to do the quality research and contribute to the nation building. So with this, the live examples here, the DRDO scientists, they kept all these models, Akash and Nag. This is the contribution of the, the scientific, the scientists, and they are helping a lot to the country. They are contributing a lot to the country. Because of, their contribution, we are flourishing, and there is a lot of scope in future also. Only thing is, everyone should put their best of the best effort towards this innovation and making all the this Vikasit Bharat objectives, should become true by 2047. For that, everyone should work in the nation building process. So I am confident that the deliberations, whatever, and technical sessions in this particular conference will generate new ideas and meaningful collaborations and impactful research outcomes. And today we are in outcome-based education system. For every program, there should be outcome, substantial outcome. Everybody should focus on outcome. I once again congratulate the organizing institutions and wish the conference great success. I thank the organizers for inviting me to preside over this prestigious event and wish all the delegates a fruitful and intellectually enriching conference. Thank you, one and all.
Thank you very much, sir, for your enlightening presidential remarks. Your inspiring message has energized us and reaffirmed the importance of innovation, collaboration, and quality research. And yes, I'm sure we all have arrived now at the absolute pinnacle of our evening. But ladies and gentlemen, before I take the privilege of introducing our esteemed chief guest of today's program, may I really request all of you to put your hands together and extend a warm, heartfelt welcome to a Padma Bhushan and a Padma Shri awardee. Please let the hall ring in. And one of India's most eminent scientists and nation builders, Dr. V.K. Saraswat.
I will give my introduction myself.
All right.
Andariki Namaskar. हमारे मंच पर मेरे बहुत सारे साथी बैठे हैं, उन सबको मेरा नमस्कार। और कुछ लोग मेरे साथ पिछले 50 साल से काम करते आ रहे हैं, उनको नमस्कार। यंग स्टूडेंट्स और फैकल्टी मेंबर्स जो यहाँ हैं उनको नमस्कार। इंडस्ट्री पार्टनर्स उनको नमस्कार। आज का दिन नमस्कार के लिए बहुत ज़्यादा इम्पोर्टेंट है। क्यों? आज जगन्नाथ यात्रा शुरू हुई। मैं यहाँ आने से पहले कंचनबाग के जगन्नाथ टेम्पल में आज एक वो दिन है जहाँ भगवान जगन्नाथ अपने टेम्पल से बाहर आके रथ में बैठ के अपने मौसी के घर जाते। तो उसमें मैंने पार्टिसिपेट किया। पर मैं हैदराबाद में हूँ, इसलिए कुछ मैं थोड़ा मसाला हैदराबाद का भी डालना चाहूँ। आप लोग मुझे बुलाए, उसके लिए बहुत बहुत शुक्रिया। और उसमें आज के इस सेमिनार में मुझे शिरकत करने के लिए आपने जो मौका दिया, उसके लिए शुक्रिया। आप लोग जानते हैं, हम लोग हैदराबाद में ऐसी ही भाषा बोलते हैं। जो लोग नहीं जानते, जो बाहर से आए हैं, उनके लिए एक थोड़ा सा उदाहरण है। हैदराबाद में मैं पिछले ऑलमोस्ट 48 ईयर से रह रहा हूँ, 46-48। मगर मुझे तेलुगु नहीं आई। क्यों नहीं आई तेलुगु? क्योंकि यहाँ पे सब लोग ऐसे ही भाषा बोलते हैं। अगर मैं विजयवाड़ा में होता, विशाखापट्टनम में होता, तो शायद आप लोगों की तरह अच्छी तरह तेलुगु बोलता। तो गलती मेरी नहीं है, हैदराबाद की है। Friends, let us come to the topic now. It's a very interesting topic today because it reminds me of my days as a student. When I was a student of engineering in 1966, 60 to 70, I was a mechanical engineering stream. We were taught electrical engineering as a subject. And in that electrical engineering, we were taught electronics also. At that point in time, the electronics was only analog electronics. There was some exposure of electronics at that time because radios used to be there. And although the radios used to be working on valves, you know, triode, diode, pentode, and all that. So we were all taught about that. The digital electronics, I don't think there was an exposure to that. When I came to Indians of Science, and there they started selling the digital electronics. Because my engineering college did not have any coverage of digital electronics in a curriculum at that time. While digital electronics had come in, but it was not being taught. Why I am giving this story? That our curriculums do not keep pace with the evolving technology. So as an institution, you have to also take care of such gaps. So there we were taught about computers. First time, I was taught Fortran 4 computer programming. And my professor Gurraj was my teacher who was taking the book of the famous IIT professor Raman, Raja Raman book for teaching us Fortran programming. From there we got exposed to digital and instrumentation class. Our teacher Malti, she is no more unfortunately, she used to teach us about digital electronics about that time. Then I came to DRDL. ISC at that time already had IBM 360 computer. I'm talking of 1970. So we got used to using IBM 360. And DRDL has only IBM 1620 computer. Generation behind. And by the time we came into this, the calculators also started coming in. The only thing that was available to 24 of the IIT and ISC graduates who had joined DRDL at that time. In my department of propulsion, there was only one Moscal calculator with a memory of 200 bytes. And even for that one Moscal calculator, we were 24 people fighting at that time. Again, what I am trying to give you is, From that, we have seen how the growth of electronics has taken place. You don't know how we used to make telephone calls. If I had to make a call, I had to go to the post office if I have a lightning call to make. And even at that time, I'll be shouting at the top of my voice to go across. Those are all mechanical exchanges. Then came Sam Petroda, C. Dot, and we have digital exchanges. And today we are talking of 5G, 6G, and so on. So that is the way growth has taken place. In the era of electronics, there has been a significant amount of growth. The first time I faced that the gap between us and the developed nation is so high was when we were trying to make the first onboard computer for our Prithvi missile. Before that, my colleagues, Ramana Sai, unfortunately he's also left us, and others, they used to use transistors to make a circuit for evaluating cos of an angle using transistors or a sine function or any other function. They used to make like that. And we have to now make an embedded computer. So obviously a transformation was required at that point in time. And these people got to using the imported, in those days available, 8086 Intel 8087. That was the device which was used. Again, I'm trying to bring that point because India had no such base. Unfortunately, even today, we don't make our own process. This is one glaring example of how we have developed our electronics. When it came down to the operating system, a real-time operating system was IRMX. IRMX version 2.0, 2.4, that was also not available to us. And even a small kernel was given to Wipro, and from there we used to get, because it was denied. And that's how the embedded system was done. So we progressed from 8086 to then 386, 486, then Pentium, and also on. And today we know what we are using for all our systems. DSPs, FPGAs, everything has happened. But one thing is still common. Everything what we are doing, whether an embedded system or a control system for e-vehicle, or we are doing a communication system, or we are doing a large-scale computer, all devices are imported. All processors imported. You had a fantastic lecture by one of the gentlemen from Cisco, if I'm not wrong. He was talking about how the growth of different kinds of switches is taking place and how the future data centers will be requiring optical interconnects and the kind of cooling systems and things like that. Obviously, there's one thing which is common. While we are learning to use the developed devices and systems for our products what we are making, but we lack as far as the hardware and software of doing that. The sovereignty for a nation, if India has to become a developed nation by 2047, as our respected Vice Chancellor of Osmania University is telling, the sovereignty is one thing which has to be taken into account. I'll give you a story. When I was in Niti Aayog, they said that you chair a committee on high performance computing systems. So when I saw the cabinet note which was made by some very esteemed people of our country, it depended on purchasing high performance computers from the market and supplying to various IITs and universities so that our scientists, engineers will be able to graduate from serial computing to parallel computing, because that was the mission. So when I saw that, I said, no, we don't want to purchase any more high performance computers. There was a lot of opposition from those who had drafted that particular cabinet note, but I prevailed, and with the help of CDEC and ISC and our industry, we changed the complete course of that. A supercomputer which was first developed by Vijay Bhatkar in CDEC, called Param at that time in early 2000, was the only thing which was indigenous at that time. And today, because of that push that we will use indigenous technology, indigenous manufacturing, indigenous application, today, my dear friends, that transformation has taken place, that 38 petaflop computing facility using, of course, the devices like chips from outside, but right from the breadboard design to complete circuit design, everything is indigenous, including the software. So that is what I'm expecting from you guys tomorrow. The sovereignty is important, friends. Another example I want to give you. For this same supercomputing mission, we said that we will make our own chip. And hence we decided that we should rope in industries, because most of the time I used to hear lectures from a large number of our esteemed scientists and also administrators that there is no chip in the world which is not having design being done in India, in Bangalore particularly. So I said, we are a great nation. If we are able to design our own chips, then why we have not done it so far? So I went to one, I won't name the company. I said, look, you make the processor for this. I want 4-core processor with more than 2 gigahertz frequency and other specifications I laid down. This should be the form factor. And I would like it to be designed by you. Those who have been doing for multinationals large number of VLSI designs, they refused to take up the task. They said, we have never designed a chip or a device ab initio from the specifications. What we have been doing is, somebody is making an interconnect, somebody is doing a communication interface, somebody is doing memory interface, and so on. So our capability was in using whatever software packages were available from our licensors to put them together and do what the multinationals want. As a result, we were not able to get what we need as a device, and that is the situation even today. So we came to Hyderabad, because I love Hyderabad, I've been in Hyderabad. There's a company called Moschip here, and I went to them, I said, can you do it? He said, sir, we don't have the core. If you get us the ARM core, we will be able to do that. So we bought an ARM core, and today our own processor using the ARM core designed by our Moschip is being done, which will be manufactured on 7 nanometer to 3 nanometer at Taiwan. Now this capability came only because we forced our own industry to do it. If you don't take that clutch, that we have to do it in India, the disruption which is coming today in the form of artificial intelligence or quantum, for which this seminar is there, will also make you completely dependent on the foreign things. I want to ask you, as I mentioned to you that real-time operating system was not there. Linux open source came and we started using Linux. Can you tell me, all of you are doing a lot of artificial intelligence. Pulak is there, somebody was telling Pulak is doing artificial intelligence. Suppose the basic software for this, what is the software today for the artificial intelligence which you are using today? Name one. Nobody is naming. Which is the software you are using? Which is the AI software which you are using today? Python. Now you can, at least somebody is saying. Where is Python of India? If Python is not there, none of you will be able to do one step on artificial intelligence. If LLM has to be done, so where is India's Python? Why India did not have its Python? All the simulation software, whether it is CFD or FEM or electromagnetics or drug design or even genomics, Gunguru was here somewhere, all these areas, biotechnology, everything is based upon software packages which is coming from outside. Our young students have been now taught to use them and then churn out some colored graphs, and those graphs will be able to see some up and down of the parameters, and we are very happy with that. But that does not give you what is called design capability. India lacks the design. If you want to make India as a strong nation, this institution has to produce designers. So if you are teaching them VLSI, teach them complete VLSI process. And all institutions should have the minimum facility for doing certain fabrication of devices. If not all, a cluster of institutions can join together and set up a center where they can go and experiment. I agree it's a costly affair. And hence, we decided that there should be, even the manufacturing of these devices should be done in India. And hence you have a National Semiconductor Mission 1.0, about which you have seen what is happening. Now NSM 2.0 with a network turnover something like 1.6 lakh crore, also being done for going now from 28 nanometer down to 7 nanometer, 2 nanometer, 3 nanometer. And also the next generation of technology like neuromorphic chips. And the advantage today is, compared to the earlier one, is that you have a RISC-V based open source software available. If you guys can make, and that's why for AI, we are not doing RISC-V based processor, and we are also not depending upon GPU people, NVIDIA. We are going to make our own RISC-V based complete GPU. So that GPU, CPU will make sure that indigenous technology is there. And if I agree, the manufacturing will still be done outside. So that has a certain vulnerability even there. But if you are able to do some system for certification and validation, I think we will be able to come out of it. Last what I want to talk about is artificial intelligence is, friends, is a good tool. But it is like a tool in the hand of a monkey. If it is not properly used, it can hurt you. Artificial intelligence for cyber security, it can enhance your capability for cryptanalysis and many things, data analytics. But the same artificial intelligence can be used by people who are attacking you, and hence they can also be smart. So we have to make sure that it should be done in a manner in which it has to be in a detailed manner, so that you can plug in. AI, unless it is explainable, unless it is responsible, is a bad tool. Whether it is for design, whether it is for translation, whether it is for manufacturing. If you are totally dependent on autonomy system with imported devices, imported software, you are the most vulnerable. In Operation Sindoor, we saw the impact of GPS being denied. Many of the systems, they started not performing because they have to depend only on the navigation system. So if you are making tomorrow a navigation system, you use now quantum technologies. The quantum is coming. This morning I gave a talk on quantum sensors. Now we have to, India has suffered on two fronts, like we have talked about electronics, materials and sensors. Even today that is the biggest weakness. The journey of sensors, which used to be based upon strain gauges and piezoelectric crystals and so on, is going now into quantum domain. If we don't do this journey, and then came MEMS and NEMS, again we missed that part. If we don't go into that today, into quantum and do it ourselves, we have difficulty. And quantum also, you will not be able to do it. How many of you have done, many of you must be learning quantum, how many of you have done a basic course on quantum mechanics? Can you raise your hand? One. That is my problem. We are all talking of quantum, we are teaching quantum our people, but we are not telling them what is coherence, what is uncertainty principle, what is decoherence. All that we are not teaching them, what is the physics behind that. And we are all talking of quantum. How the spin is taking place, how a coherent entanglement happens, even if the two photons are sitting at distance of 1 kilometer. How will it happen? How it is happening? Duality, nobody is explaining. So the basics of quantum physics has to be understood by all students before you get into that. And I request my principal sitting here, your curriculum, at least the one or two, one semester, you teach them the basic quantum physics, quantum mechanics, then only you take them into technology domain. I hope this conference will throw up such good ideas. It will give you a window for working for future, because the future for the growth of the economy is dependent upon the disruptive technologies. And disruptive technologies are growth in high performance computing, quantum communication, quantum materials, quantum sensors, and artificial intelligence and quantum working together with manufacturing technologies for devices, with new materials, 2D materials, nanomaterials, all put together. In the processes which were not thought of earlier, they have to be taught to each one of them. Skills have to be generated. It is said that if India's 1,60,000 crore worth of semiconductor facilities come in, where are the people, where are the trained people who will be able to man it? Where are the instruments? For example, our Honorable Prime Minister went to Netherlands. You know why did he go? Because ultra precision photolithography machine, UVL, manufactured only by Netherlands, ASML. Today there is a queue for it that you have to wait for 3 years. This is the kind of choking that is taking place. Dilution refrigerator for your quantum computing. It is requiring a delivery time from foreign countries of 8 months to 1 year. Now what is difficulty in doing these things in our country? Because we have not given a product focus. We have given only a focus to science of engineering. Sir, science of engineering is required. We have done it for last 75 years. We need to do, along with that, the technology. And if we don't do technology, we will always remain a nation of assemblers, but we will not be a nation of product developers. Innovation with product development, self-reliance, sovereignty in materials and software and hardware. If it is not there, India will remain underdeveloped, really, but your economy still may grow. You may have a trillion economy, but you can be choked anytime. There could be an equivalent of Strait of Hormuz in your technology stream. Please don't wait for that. Let's work for self-reliant India in electronics, communication, engineering, artificial intelligence, and quantum. I wish you all the best, that you will be able to achieve your best in this conference and drop a roadmap for how the students of tomorrow will be trained for the future technology. Thank you very much. God bless you all.
Thank you so much for such an exceptional, remarkable, visionary roadmap for all of us. And now it's time for us to release our conference souvenir. Thank you, sir. It is absolutely.
I request all the dignitaries on the dais to kindly release the official ICESAIS 2026 conference souvenir.
We request all of you to put your hands together because it's official release of our conference souvenir. Our first step towards making our international conference a grand success. We thank all our dignitaries on the dais for the honors. And now the last milestone of this program. Our absolute honor to express our deep gratitude through our formal felicitation ceremony. And may I now take this honor and privilege to request our management dignitaries, Mr. K. Krishna Rao Garu, Secretary and Correspondent, Shri Rakesh Reddy Garu, Dr. B. L. Raju Garu, Professor Prabhuji Benekop Garu, to kindly felicitate our esteemed guests with a token of love and appreciation. And today's presidential address, presidential remarks, our beloved chief guest and Dr. V.K. Saraswat Garu. I would wish everybody to please put your hands together because it's a token of gratitude, their time, love and appreciation. Lovely. Thank you so much, sir, for your valued presence here today. Thanks for your time. And now, the president of the program today, Professor Senior Academician Kumal Molagaram Garu. Please put your hands together as a token of our respect, their time, their presence. We are deeply indebted to our chief guest today and our president for the program. Thank you so much, sir, for your valuable time and your dedicated being with us. Thank you so much, both of you. It was a pleasure having you today.
Up next, we request our management to kindly facilitate the guest of honor, Sri Raja Babu, former Director General, DRDO. Thank you very much, sir, for being an inspirational source. Now, to conclude, we request our management member to kindly felicitate the tech ecosystem pioneer, Shri MGPL Narayana, Chairman of the IEEE Hyderabad section. Thank you, sir. Put your hands together, please. Thank you, sir, for your continuous encouragement and spearheading engineering community with such vigor. Thank you so much. Now we request the management to kindly present a token of appreciation to our legendary conference advisor, Dr. S.K. Chowdhury, former director, RCI, DRDO. Thank you very much, sir, for being the source of inspiration to everyone in the conference. Thank you.
Right, to wrap up this historic inaugural session, we invite Professor VSSN Srinivasa Baba, Head Department of ECE, MCET, to deliver the formal vote of thanks.
Thank you. It's my proud privilege and distinct honor to propose the vote of thanks on the memorable occasion of the inaugural session of the IEEE International Conference on Electronic Systems and Artificial Intelligence Applications, ICESAIS. On behalf of the organization, Methodist College of Engineering and Technology, Stanley College of Engineering and Technology for Women, Avionics Society of India, and our technical sponsor, IEEE Hyderabad section, I extend our heartfelt gratitude to everyone who has contributed to making this inaugural ceremony a grand success. First and foremost, we offer our deepest gratitude to Rajababu sir, SK Chaudhary sir, MGPL Narayana sir, for your continuous support and significant contribution for the success of this conference. We also respectfully thank our beloved Secretary and Correspondent Krishna Rao sir, our Rakesh Reddy sir, Director Infrastructure, for their continuous encouragement. Thank you, sir. I extend my sincere appreciation to our General Chairs, Dr. B.L. Raju, Principal, Stanley College, and Professor Prabhuji Benkop, Principal, Methodist College. Your exemplary leadership, meticulous planning, and tireless efforts have transformed the vision into reality. The conference is the outcome of dedicated efforts of numerous individuals working tirelessly behind the scene. I extend my heartfelt appreciation to all the members of the Advisory Committee, Technical Program Committee, Publication Committee, Organizing Committee, Session Chairs, Reviewers, Faculty Members, Administrative Staff, Technical Staff, Volunteers, and the other enthusiastic student coordinators. Your commitment, teamwork, and professionalism deserve our highest appreciation. I acknowledge the partnership, our industry partners, Qualcomm, Ananta Technologies, Electronic Circuit Systems, Air Force, Ecutronics, sponsors, IEEE volunteers, media representatives, and every organization that has extended their valuable support to the conference. My sincere thanks goes to all the others, researchers, academicians, industry professionals, delegates, participants from India and abroad for contributing to the conference. Finally, I thank every one of you present here for your gracious participation in making this inaugural ceremony truly memorable. As we conclude this formal inauguration session, I warmly invite all of you to stay engaged in the technical sessions over the next 2 days, interact with fellow researchers, exchange ideas, and build lasting collaborations. May I now request everyone to kindly rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
जय हिंद।